When was the last time NASA went for months without showcasing new images from the James Webb Space Telescope? When has the Hubble Space Telescope ever captured something extraordinary and then simply ceased to discuss it? These questions highlight an unsettling reality surrounding our third confirmed interstellar visitor, 3I Atlas. This cosmic wanderer arrived in July bearing characteristics that stirred up far more questions than answers. Initially, we were treated to a steady stream of updates and breathtaking imagery, fueling our curiosity and wonder. But then something changed in August. The once vocal space agencies and telescopes suddenly went silent. Hubble's observations ceased, and Webb's spectroscopic data disappeared into a limbo of silence, leaving us with only vague, overly rationalized updates from NASA that offer little insight. Even as Atlas draws closer to its closest approach with Mars, a celestial event that could provide crucial close-up observations, the institutions we rely on to reveal the universe's secrets have retreated behind a wall of silence. This raises a profound question. What is truly happening behind the curtains? What discoveries have they made that they are intentionally withholding? Tonight we delve into the chilling theories behind this abrupt absence of new images and information. More troubling still is the most terrifying possibility no one is openly discussing. The idea that something unprecedented, perhaps even alarming, has been captured during those missing weeks. Let's begin with what we know, or rather what we don't see. Part 1. The missing images. Behind the scenes, something appears to be fundamentally wrong. As of September 22nd, the most recent publicly available data from our flagship telescopes paints a troubling timeline. Hubble's last publicly released image of Atlas was taken on July 21st and made available to the world on August 7th. The James Webb Space Telescope, which observed the object on August 6th, has only released spectroscopic notes with no accompanying images. Meanwhile, a single image from Gemini South, released on September 4th and 5th, was actually taken on August 27th. Stop and consider that for a moment. Our most powerful eyes in space, capable of revealing the faintest details of distant objects, have essentially gone silent on the most intriguing object to visit our solar system in years. The official NASA explanation for this silence is straightforward. After September, the comet's visibility from Earth diminishes because it draws too close to the Sun, placing it behind a solar conjunction that makes observation difficult. It's a scientifically sound explanation, an understandable natural obstacle to observation. But does it truly justify the absence of new imagery, or is there something more beneath the surface? Let me lay out a timeline that should unsettle anyone who has been closely following space exploration developments. On July 21st, Hubble captures what becomes its final publicly available image of Atlas. Then, on August 6th, Webb observes the object but only releases spectroscopy data, not images. Later in August, Gemini South manages to take some imagery, but that data remains unreleased until early September. As of September 22nd, the public eagerly awaits new images from our most advanced telescopes, nearly 2 months of silence. This prolonged period of observational quiet from the very instruments we depend on to explore the cosmos is unprecedented in recent memory. Theories circulating among certain circles suggest that this silence isn't accidental. What if, during those missing weeks, something too strange, too extraordinary was captured? Could the images exist hidden away because they threaten to challenge everything we've come to believe about comets, interstellar visitors, or what's possible in the dark expanses between stars? The suspicion is that the images are held back, not because of technical difficulties or routine observation gaps, but because they contain truths so startling that revealing them might shake the very foundations of our understanding of the universe. This possibility ignites a sense of unease. a sense that perhaps we are being kept in the dark about something profoundly important. As Atlas approaches its close encounter with Mars, the silence from our most powerful observational tools has only grown more deafening. The question remains, what is really happening behind the scenes? And what have they captured that they are deliberately choosing not to show us? Comets, those icy wanderers from the dark, uncharted regions between stars, hold many secrets about our universe's most elusive boundaries. They serve as messengers from the depths of space, offering clues about what's possible in the unseen interstellar realm. Yet amidst these grand mysteries, it's important to acknowledge the straightforward, more mundane explanations that often explain gaps in our observation. Time on powerful telescopes, for instance, is incredibly valuable. It is meticulously scheduled months in advance, with every moment of observation carefully planned and allocated. The pipelines used for analyzing data from major observatories are slow, methodical, and deliberate. Scientists prefer to fully understand what they are seeing, interpreting complex spectral signatures and subtle signals before sharing their findings with the broader public. The vast and unforgiving geometry of space often plays a role as well. Objects can become difficult or even impossible to observe from Earth's vantage point at certain times, especially when they align behind the sun or move into regions of the sky that are inaccessible. These are rational, scientifically grounded reasons for any extended absence of new imagery or data. However, despite these rational explanations, the reports we do have from mid-September tell a different story, one that suggests something extraordinary. Amateur astronomers observing with smaller, more accessible equipment have reported that the object in question appears to be brightening at a rate faster than any model predicted. They claim it has increased in brightness by multiple magnitudes far beyond what our initial expectations would have allowed. Of course, these claims originate from non-professional observers whose estimates have yet to be peer-reviewed and officially confirmed by the scientific community. The possibility of error is real. Observer mistakes, differences in instruments, or measurement inconsistencies could all explain the discrepancies. But what if these reports are accurate? What if this object truly is behaving in a way that defies our current understanding? With the approach date of October 3rd just days away, the urgency is mounting. This date marks the closest pass of the object to Mars, offering our best chance for an up-close, ground-truth observation. Such a mission could either verify or dismantle the swirling theories that surround this mysterious visitor, truths that have only grown more complex as the weeks have gone by in silence. The clock is ticking. The Mars orbiters, equipped with high-resolution cameras and spectrometers, represent our prime opportunity to gather definitive data. Their observations could provide the clarity needed to either confirm our fears or reinforce our understanding. You have the right and the responsibility to weigh the solid scientific evidence against the unsettling speculation circulating online. You deserve to see all the available data, both the reassuring and the alarming, and to draw your own conclusions about what it might mean. The question is not simply whether scientists are withholding information, it's whether the silence itself has become a form of communication, more revealing than any image or report could ever be. Looking back at previous interstellar visitors, we see contrasting approaches. Oumuamua dominated headlines with constant updates, evolving from an enigmatic object into a media sensation, with steady streams of images and interpretative reports. Borisov, on the other hand, behaved more conventionally, fitting neatly into our existing models of comets, and was shared openly, comfortably with the public. But Atlas feels different. Its coverage has been cautious, measured, and deliberate. Why? Perhaps because something about it challenges our expectations, anomalous enough to warrant a more careful, restrained approach. Soon, the Mars orbiters may break this drought of silence with close-range images that could change everything. The critical question now is whether these images, when they arrive, will be shared with the same transparency we've come to expect from space agencies. Or will the pattern of selective silence persist, leaving us to wonder what wonders or horrors are being filtered out of our view of the cosmos? Mars Express, the ExoMars Trace Gas Orbiter, and potentially NASA's Mars Reconnaissance Orbiter, if the current orbital geometry permits, stand as humanity's prime tools for obtaining detailed, high-resolution imagery of Atlas before it continues its silent voyage toward the Sun. This window of opportunity, though narrow, is arguably our best and perhaps our only chance to peer closely at this mysterious interstellar visitor in its current phase. As Atlas approaches perihelion, the point of closest proximity to our star, scheduled for late October, specifically on October 29th and 30th, the planet-bound observers eagerly anticipate what might be revealed. During this period, Atlas will be within roughly 1.36 to 1.4 astronomical units from the Sun, just inside Mars's orbital path, placing it in a region where comets have historically dazzled with their most spectacular displays. The Sun's intense heat in this zone typically ignites dramatic outgassing events, generating the brilliant comas and shimmering tails that have long captivated astronomers and laypeople alike, weaving stories of cosmic wanderers that dance across our skies. Yet Atlas has already begun to challenge these expectations in ways that continue to baffle scientists. NASA has been explicit in assuring the public and the scientific community that Atlas poses no threat to Earth. Its closest approach to our planet is expected in December, at a distance of about 1.8 astronomical units, far beyond the Sun's position, meaning that we are mere spectators, passive witnesses to a celestial drama unfolding in the vastness of space. We are observers, not participants, in what could be a historic event that might reshape our understanding of interstellar objects. What truly elevates Atlas from a mere curiosity to an object of profound scientific interest is its unusual composition and behavior. The Sphere-X mission, equipped with advanced spectroscopic tools, has detected something utterly unprecedented: a colossal carbon dioxide coma extending outward for approximately 348,000 kilometers. To grasp the scale of this gaseous shroud, consider that it spans roughly half the radius of our Sun, an immense gaseous envelope that defies everything recorded in cometary science. No comet in recorded history has exhibited such an expansive CO2 atmosphere, making Atlas a phenomenon without precedent. The morphology, the shape and structural features of this object also defy traditional expectations. Images from the Hubble Space Telescope, complemented by ground-based photographs, depict a startling feature: a sun-facing plume, an anti-tail that points directly toward our star rather than away from it. This is a direct contradiction to the well-understood physics of solar wind pressure and radiation effects, which typically cause comet tails to stretch away from the Sun. The physics we rely on tell us that solar radiation and solar wind should push dust and ionized particles away from the Sun, creating a tail that always points in the opposite direction. Yet Atlas's anti-tail not only points sunward but appears to be a persistent feature, raising questions about the dust grain sizes, the rotation rate of the object, or its internal structure. Factors that might be generating patterns we simply cannot yet comprehend. Adding to the enigma, reports began emerging in late August and early September of a color change in Atlas's coma. Observers noted a subtle greenish tint developing around the object, a detail that hints at complex chemical processes. The likely culprits are energized dicarbon molecules or cyanide compounds which could fluoresce under solar radiation, imparting a green hue. However, this intriguing coloration remains unconfirmed through rigorous spectroscopic analysis. Instead, our knowledge relies on visual impressions, photographic evidence, and educated guesses about the chemical makeup, which may or may not accurately reflect the true composition. Perhaps most unsettling of all is the brightness behavior of Atlas, which has been intensifying faster than models predicted. Earth's skywatchers, along with various astronomical outlets, have compiled reports from both professional and amateur observers, noting that the object appears to be brightening more rapidly than anticipated as it moves inward, within about 2 astronomical units of the Sun. The numbers, however, vary widely depending on the aperture sizes of telescopes, the filters employed, and the observing conditions. This inconsistency is not unusual in amateur astronomy, where scattered data points often require careful statistical analysis to interpret accurately. Many of the most recent images, in fact, have been produced by amateur astronomers stacking multiple exposures to tease out faint details, a process that introduces its own uncertainties but remains invaluable for early detection of anomalous activity. This discordance in brightness measurements points to a deeper issue, one that challenges our ability to reliably interpret the behavior of such an extraordinary object. Despite the widespread use of high-powered telescopes, some of the latest images come from dedicated amateur astronomers who combine multiple images to enhance faint signals. These efforts, while invaluable, highlight the difficulties in establishing a definitive understanding of Atlas's current state, especially when the professional observatories, which should be able to provide more precise and systematic data, have been comparatively silent during this critical phase. The most advanced and reliable telescopes in our arsenal, those that should be delivering precise, conclusive data, have remained conspicuously silent. These formidable instruments, equipped with sophisticated pipelines designed to process and analyze data meticulously, often operate at a measured pace, especially when objects drift toward the sun's glare, a period known as solar conjunction. During this phase, observational efforts become inherently complex and technically demanding, requiring careful calibration and timing. Consequently, the schedule for releasing new data becomes a delicate balancing act, often resulting in a perfect storm of uncertainty and silence. While the wider community of amateur astronomers eagerly shares their latest images and observations on social media within hours or days of capturing them, professional facilities often delay public disclosures for weeks or even months. These delays are due to rigorous analysis, verification procedures, and peer review processes that safeguard scientific accuracy, but also contribute to a growing gap between citizen science contributions and official institutional reports. Never before has this chasm felt so stark and pronounced as it does now, with the mysterious interstellar visitor known as Atlas. Indeed, scientists at the European Space Agency have publicly indicated that the spectroscopic data collected by the James Webb Space Telescope on August 6th remains under detailed analysis. What could they be uncovering in those spectral lines? What chemical signatures are so intricate or unexpected that their full interpretation demands extended study before any formal publication? The persistent silence surrounding these results feeds suspicion and fuels speculation. Could it be that something genuinely unforeseen, perhaps even unprecedented, has been observed? The trajectory of Atlas itself aligns remarkably close to the ecliptic plane, the vast disc-shaped region in space where most planets orbit the Sun. This precise alignment is no mere coincidence. It facilitates a close encounter with Mars set for early October and hints at a future flyby of Jupiter in 2026. Such meticulous orbital positioning appears almost crafted. Yet natural orbital mechanics can produce such surprising and seemingly deliberate geometries through gravitational interactions and celestial dynamics over vast timescales. As humanity teeters on the brink of the Mars flyby, The accumulation of unresolved mysteries surrounding Atlas creates an atmosphere thick with anticipation, tinged with a sense of unease. The absence of recent images from our most capable telescopes, the ones capable of revealing detailed surface and compositional features, stands out starkly. The unprecedented scale of its carbon dioxide coma, stretching hundreds of thousands of kilometers, and the bizarre anti-tail behavior, where the tail points toward the sun rather than away, are phenomena that challenge our usual understanding of cometary physics. Coupled with the uncertain evolution of its brightness over time, each of these observations in isolation might be explained within the framework of conventional comet science. However, when viewed collectively, they form a pattern that defies easy explanation and questions the very nature of what we expect interstellar visitors to look like. These anomalies taken together compel us to reconsider our assumptions and to ponder whether we are witnessing something truly extraordinary. Perhaps something that pushes the boundaries of current scientific knowledge. In the third part of this exploration, why the silence surrounding Atlas matters deeply, it's essential to recognize the power of memory and expectation. Our minds can deceive us, especially when we've become conditioned to the consistent release of space imagery. Recall Comet Neowise in 2020 when social media was flooded nightly with dazzling photographs of its luminous tail stretching across the sky. Or remember the Bennu asteroid sample return mission where hundreds of images documented every step as the spacecraft approached, touched, and departed from its rocky target. An unmissable real-time window into cosmic exploration. This history of visual documentation has set a standard, an expectation, that every major cosmic event should be accompanied by a stream of images and data, shared openly and promptly. Yet Atlas feels different. The releases from Hubble and Webb have been sparse, measured, and carefully curated. More like a slow drip feed than a flood of visual information. Since August, the flagship observatories have effectively adopted what can only be described as a visual fast, a deliberate pause in releasing images or detailed data. While such caution is not entirely unprecedented, since telescope time is incredibly valuable and observational decisions are made with rigorous scrutiny, the silence surrounding Atlas's apparent significance is deafening. NASA's own official documentation explicitly acknowledges a gap in visibility after September, primarily due to the sun's glare, a technical and understandable obstacle. But the absence of recent images, especially given Atlas's intriguing characteristics, fuels a sense of mystery and suspicion. This deliberate silence, whether driven by technical constraints or strategic caution, underscores how much our understanding and our trust hinges on the timely and transparent sharing of scientific discoveries. When that flow of information slows or stops at a moment of intense curiosity, it leaves a void filled by speculation, conjecture, and sometimes unwelcome assumptions. The challenge posed by solar conjunction renders Earth-based observations of interstellar objects like Atlas temporarily difficult or outright impossible. Naturally, such periods are expected to produce a lull in data collection, which should, in theory, be understood as a routine part of astronomical research. However, what makes this lull particularly problematic is that it opens a dangerous void, a space where information is absent, and human psychology naturally fills it with speculation and suspicion. During these moments of silence, conspiracy theories tend to proliferate rapidly, especially within online forums and social media echo chambers, where the absence of official updates is interpreted as evidence of concealment. When trusted channels such as the Hubble Space Telescope or the James Webb Space Telescope go quiet, especially during times of heightened public interest, many interpret this as a sign of a cover-up, a deliberate withholding of information about something extraordinary or even threatening. The delay in releasing Webb's spectroscopic data, for example, is often spun into proof that scientists have discovered something far too strange or sensitive for public disclosure. In this context, rational explanations that observational gaps are simply due to technical constraints, scheduling priorities, or the natural timing of celestial geometries often lose ground to more sensational narratives. The international community, including the European Space Agency, did release the Gemini South image of Atlas on August the 27th, which was subsequently shared with the public in early September. This fact demonstrates that the astronomical community is not engaged in a complete, deliberate silence. Information does get out. Yet the public's expectations have been conditioned over decades to anticipate a steady stream of high-resolution portraits from Hubble or revelatory infrared images from Webb. When those sources pause, even for a brief window, it feels to many as if they've been abandoned, left in the dark just as the object's mysteries deepen. Media coverage patterns further reveal the complex dynamics behind this silence. While Atlas drew significant attention in July and August, by September a noticeable shift occurred as the focus of public and media interest transitioned toward other celestial phenomena. Comet Lemon's brightening and visibility became headline news, and the dramatic fragmentation of Comet Swan provided striking imagery that captivated the public's imagination. To those particularly tuned into Atlas, this shift might seem like an intentional distraction, a strategic move to divert attention from the ongoing mystery. In reality, it more likely reflects the natural ebb and flow of astronomical news cycles where media outlets tend to highlight visually spectacular or easily comprehensible events. Conspiracy thinking, however, thrives on the perception of patterns, on the idea that multiple unusual events occurring simultaneously are interconnected, whether they truly are or not. When the behavior of comets deviates unexpectedly, telescope coverage diminishes and media interest shifts elsewhere. Pattern-seeking minds connect dots that might not have any genuine correlation. The timing of Atlas's conjunction period, coinciding with the peak of public enthusiasm for its upcoming Mars flyby and perihelion, only amplifies this tendency. Meanwhile, the processes behind scientific analysis are inherently cautious. Major observatories prioritize accuracy and reliability over rapid dissemination, unlike amateur astronomers who can publish images within hours of capturing them. Institutional astronomy involves peer review, calibration, and careful interpretation before any findings are made public. This necessary prudence is designed to safeguard scientific credibility, but it also creates gaps, deliberate pauses that leave space for speculation to fill the vacuum. In recent years, public trust in scientific institutions has become more fragile. Debates over climate change, controversies surrounding pandemic responses, and other widely covered issues have complicated the relationship between expertise and public understanding. When agencies remain silent during periods of high interest, regardless of legitimate technical reasons, this silence tends to activate skepticism. People begin to question whether there is something they are not being told, fueling suspicions of a cover-up, not necessarily because of any concrete evidence, but because of the pattern of silence itself. The core question is not necessarily whether organizations like NASA or ESA are hiding something dramatic about Atlas. Instead, it's about how the pattern of silence influences perception. In an age where information is abundant but trust is fragile, even routine delays or technical constraints can be misinterpreted as signs of concealed truths. This phenomenon underscores how human psychology responds to uncertainty. When official explanations are absent, the mind seeks explanations, often more sensational and sometimes more frightening than reality. Thus, the current situation exemplifies a broader challenge: managing expectations and perceptions in a landscape where the absence of information can be as powerful as information itself. While rational factors, such as the need for careful analysis, the constraints of scheduling, and the natural geometry of celestial mechanics, are valid reasons for delays. They are often overshadowed by the narrative that something hidden or forbidden is being kept from the public. The delicate balance between scientific caution and transparency becomes a battleground where human fears, skepticism, and curiosity collide. The central dilemma revolves around whether the perception of secrecy has become more damaging than any actual classified information might ever be. In today's age of social media, where instant communication and widespread connectivity dominate, the absence of evidence often transforms into something far more powerful. Evidence of absence, or even worse, evidence that something is being deliberately hidden from public view. The collective psyche has become conditioned to interpret silence or gaps in information as confirmation of concealment, fueling suspicion and fueling conspiracy theories. What the public craves now is straightforward and visceral. Clear, high-resolution images of Atlas as it nears its crucial encounters with Mars and its subsequent perihelion passage. These images should vividly depict the current state of the object, revealing details of its evolving coma structure and any potential changes in its peculiar anti-tail behavior. Over the weeks of relative silence, the desire for visual confirmation of Atlas's mysterious nature has only intensified. The human appetite for tangible visual proof has grown exponentially, especially when official channels have remained reticent or silent. However, the expectations of scientists involved in the investigation are far more complex. Their focus is on acquiring detailed spectroscopic data that can definitively confirm the chemical makeup of the enormous carbon dioxide-rich coma surrounding Atlas. They seek precise measurements of the nucleus's size and its rotation period, along with an understanding of the physical processes responsible for creating the sun-facing plume and its bizarre anti-tail phenomenon. Achieving these scientific objectives requires patience, meticulous analysis, and often multiple observational campaigns across different instruments and locations to build confidence in the findings. This stark contrast, public hunger for immediate, visually compelling images versus the scientific community's need for rigorous, detailed analysis, creates an environment ripe for misunderstanding. It provides fertile ground for conspiracy theories to flourish, as every day that passes without new official imagery becomes another piece of evidence in the minds of skeptics that something is being deliberately kept from the public eye. The growing anticipation surrounds upcoming observations from Mars orbiters, which could soon deliver breakthrough images capable of either satisfying the public's curiosity or deepening the mystery further. The haunting question that persists throughout this entire saga is whether these anticipated images, once they are finally released, will be shared with the transparency and immediacy that the public expects and deserves, or whether new reasons for caution, further delays, and extended silence will emerge, thus prolonging an already excessive period of uncertainty. The longer this silence persists, the more difficult it becomes to distinguish between legitimate scientific caution and intentional concealment. This leads us into the realm of theories behind the silence. To understand the possible reasons why Atlas's imagery remains elusive, it's instructive to start with the simplest, most mundane explanations, those rooted in the technical realities and operational constraints faced by our most advanced observational instruments. Chief among these is the issue of solar elongation. As Atlas approaches its conjunction with the Sun from Earth's perspective, the geometry of observation becomes increasingly problematic. Telescopes on Earth and in space find it difficult, if not impossible, to point toward the object without risking damage to their sensitive components. For instance, the Hubble Space Telescope enforces strict pointing restrictions designed to protect its cameras and spectrographs from the intense solar radiation. During periods when Atlas is too close to the Sun in the sky, what astronomers refer to as the solar elongation angle, These instruments are effectively barred from observing the object, creating dead zones in coverage where even the most intriguing targets become temporarily inaccessible. Adding to these challenges is the reality of scheduling. Modern space telescopes like Hubble and the James Webb Space Telescope operate on meticulously planned observation schedules that are set months or even years in advance. While there are provisions for target of opportunity observations, emergency or highly unusual events that justify interrupting the regular schedule, the criteria for such interruptions are strict. These are typically reserved for phenomena of exceptional scientific importance, such as supernova, gamma-ray bursts, or asteroid impacts. Not for objects that, while unusual, do not meet the high threshold for urgent observation. In the case of Atlas, despite its extraordinary characteristics, it may not have qualified for emergency observation time. Its appearance, though rare and intriguing, might not have been deemed scientifically urgent enough to justify breaking into the carefully crafted schedules of these powerful observatories. Consequently, the delays and gaps in imaging and spectroscopic data are not necessarily signs of concealment, but could simply reflect the logistical and operational realities of contemporary astronomical research. The process of scientific analysis inevitably introduces delays that impact the dissemination of major astronomical discoveries. State-of-the-art telescopes, such as the James Webb Space Telescope, generate data that must undergo a meticulous series of procedures, rigorous processing, calibration, and detailed interpretation, before they are deemed suitable for public release. Unlike amateur astronomers who can immediately share raw images within hours of capturing them, professional astronomical institutions adhere to strict protocols that involve peer review, quality assurance, and verification before any findings are shared openly. This ensures the accuracy and reliability of the information, but also extends the timeline significantly. Take, for example, the spectroscopic observations of Atlas captured by Webb on August 6th. These measurements are likely still being analyzed within extensive data pipelines, with scientists meticulously examining each spectral line to interpret the chemical signatures and physical properties of the object. Every step involves careful, deliberate work, balancing scientific rigor with operational constraints, which further complicates timely disclosure. The data from Webb's near-infrared spectrograph on that date isn't just a single piece of information. It forms part of a broader, complex puzzle of observations that require synthesis and validation. It's important to recognize that not every scientific measurement results in the kind of visually compelling images that captivate the general public. Spectroscopic data primarily reveals the composition and physical conditions of celestial objects, details that are crucial for understanding their true nature but don't necessarily produce the dramatic visuals often associated with space exploration. Consequently, a significant gap often exists between the initial collection of scientific data and the release of images or visual summaries suitable for public consumption. This gap can stretch across weeks or even months, especially when multiple observations, analyses, and peer reviews are involved. Venturing into more speculative territory, though it must be emphasized that these ideas are clearly labeled as conjecture. Certain theories have gained traction within online communities that closely follow Atlas's behavior. One such hypothesis, often called the panic prevention theory, suggests that space agencies might intentionally delay releasing certain visuals if they appear too anomalous or difficult to interpret without risking public alarm. Imagine that Atlas's anti-tail behavior, which defies conventional physics, evolves into something that looks explicitly artificial or structured, an unmistakably engineered form rather than a natural celestial phenomenon. Would agencies like NASA rush to share such images without first constructing explanatory frameworks to help the public understand what they're seeing? This theory presumes a paternalistic approach to cosmic information, where experts and authorities filter and control the flow of revelations to prevent misunderstandings, panic, or misinterpretation. It raises the possibility that agencies might deliberately hold back certain imagery to avoid triggering fear or confusion, especially if the visuals suggest something profoundly unusual or potentially artificial. Adding another layer to this complex picture are national security considerations. Military surveillance systems, which operate with capabilities far beyond civilian observatories, undoubtedly track bright objects like Atlas with high resolution and continuous monitoring, often with better temporal coverage. However, data gathered through classified military channels rarely become publicly accessible, even when they pertain to scientifically significant targets. This creates a substantial discrepancy, a gap between what classified high-resolution imagery might reveal and what the public is permitted to see. Such an imbalance fuels speculation about what additional insights could be gleaned from more advanced or sensitive sources. Some proponents of this line of thought argue that during conjunction periods, times when Atlas's trajectory aligns with the Sun, agencies might anticipate increased observational difficulties, both technically and in terms of public visibility. Instead of repeatedly explaining the technical constraints that hinder imaging, they might prefer to simply wait out the period of poor visibility and then resume observations once the risks and complications diminish. This approach would be more about managing the narrative, maintaining silence during the conjunction rather than continuously defending the absence of new imagery, thus avoiding the repeated need to justify observational setbacks. It's worth noting, however, that not all evidence supports the idea of complete suppression. The record remains clear that some imagery has been publicly shared. For instance, the Gemini Observatory released their images taken on August 27th in early September. This demonstrates that the full suppression of Atlas's visual data isn't the case. Some images do see the light of day, indicating that the situation is more nuanced than a blanket cover-up. It suggests that while delays and cautious releases are common, they are not necessarily indicative of a deliberate attempt to conceal the object's true nature, at least not entirely. Scientific professionals continue their diligent discussions about Atlas at academic conferences and through peer-reviewed publications. The ongoing pursuit of knowledge persists unabated, even as recent public imagery and direct visual updates have noticeably diminished. This pause in visible communication can often be attributed to strategic choices in equipment deployment rather than any sinister intent. As Atlas draws nearer to the period of conjunction with the Sun, observatory and telescope operators are likely prioritizing their limited resources toward targets that are more straightforward to observe, those still accessible without the complications introduced by increasingly challenging solar elongations. Such planning exemplifies prudent operational management rather than deliberate concealment. Furthermore, the inherent complexities of international collaboration could also be a significant factor behind the delays in releasing new data. Multiple space agencies and research institutions around the world are independently engaged in studying Atlas, each following their own protocols for data analysis, peer review, and public communication. Coordinating the timing and content of public disclosures across these diverse organizations naturally introduces logistical delays, especially when each entity has its own procedures and standards for validation and PR. This mosaic of independent efforts suggests that the apparent silence is more likely rooted in the realities of bureaucratic and operational logistics than in any attempt at hiding information. When we distill these considerations, a clear picture emerges. The most plausible explanation for the current lack of detailed imagery from Atlas is rooted in practical constraints, namely, the limits of observational capacity, scheduling priorities, and the complexity of international coordination, rather than a covert effort to withhold information. Nonetheless, this period of quiet, coinciding with the peak of public interest and curiosity, inevitably fuels speculation and the proliferation of fear-driven theories. The absence of recent images during such a critical window leaves room for narratives that interpret this silence as evidence of concealment, whether justified or not. The disconnect between what can reasonably be explained and how the public perceives it has become as compelling as Atlas itself. This disparity is amplified by broader patterns of information management observed in other contexts, ranging from reports of unidentified aerial phenomena to responses during global health crises, where authorities and organizations have often adopted a strategy of selective disclosure. Such approaches have conditioned the public to expect, or at least accept, that complete transparency is unlikely, and that some level of information control is standard practice. This expectation shapes how many interpret gaps, delays, or absences of data in official communications about extraordinary phenomena. As humanity prepares for upcoming observations during the Mars flyby, the weeks of relative silence have created an environment of heightened scrutiny. Any new images or data released during this period will be dissected not only for the content they reveal, but also for potential signs of omission or editing, intentional or otherwise. This perception of secrecy, whether rooted in reality or simply in the collective imagination, has itself become woven into the story of Atlas, shaping narratives and influencing public perception. Part 5. Governments and Space Control. The infrastructure governing space communication operates through a network of carefully designed channels, complex, multi-layered, and often opaque to those outside the core scientific community. NASA, for example, adheres to a mission mandate that emphasizes transparency. But the timing and framing of its press releases and public statements are subject to meticulous curation. This process aims to balance the imperative of scientific accuracy with the need to sustain public interest and avoid misinformation. Similarly, the European Space Agency employs comparable protocols, striving to maintain transparency while ensuring that information is properly vetted and contextualized within rigorous scientific standards. While these systems function effectively during routine discoveries, they tend to encounter friction during episodes of intense public curiosity, particularly when it concerns anomalous objects like Atlas. The situation becomes even more complex when classified sensors and military systems are involved. The Department of Defense operates an array of tracking and monitoring systems designed to oversee space for potential threats, debris, and unidentified objects. These capabilities often extend to bright, fast-moving objects such as comets and asteroids, providing resolution and coverage that surpasses civilian telescopes. Yet the data gathered by these military assets remains largely inaccessible to the public and scientific community, adding a layer of opacity to the overall observation ecosystem. This compartmentalization of space surveillance, where civilian agencies operate openly but military and intelligence assets function under a veil of secrecy, can fuel suspicions about what information might be withheld. The disparity in resolution, coverage, and access between military and civilian systems means that some of the most detailed and potentially revealing data about objects like Atlas could be confined within classified channels, further complicating the public narrative and fueling speculation about hidden knowledge. The divide between the advanced observational tools kept under strict classification and the information openly available to the public creates a fertile environment ripe for speculation about the existence of more detailed imagery. Images that might indeed exist but are deliberately concealed from view. This situation closely mirrors recent debates surrounding the transparency of unidentified aerial phenomena, or UAPs, a topic that has gained significant traction in public discourse. Historically, government agencies have adopted a cautious, step-by-step approach to revealing information about such phenomena. opting for a gradual release of data rather than full, immediate transparency. This pattern of carefully managed disclosure has inevitably shaped public expectations about how extraordinary space events, particularly those involving anomalies or unknown objects, are likely to be handled and presented. If encounters involving military pilots and unexplained aerial objects often require years of bureaucratic processing, verification, and cautious approval before any acknowledgement is made, one might reasonably question what kind of timeline will govern the release of observations related to anomalous comets or interstellar visitors. During September, media coverage specifically related to Atlas has noticeably waned. Whether this decline signifies a natural ebb and flow typical of news cycles or reflects more deliberate, coordinated editorial decisions remains uncertain. Headlines have increasingly shifted their focus toward other celestial objects, such as Comet Lemon, whose trajectory and brightening are predicted to make it visible to the naked eye by late October, as well as the dramatic fragmentation of Comet Swan, which provided visually stunning imagery in real time. Meanwhile, coverage of Atlas, the object approaching its close encounter with Mars, has diminished despite the mounting scientific significance of its upcoming passage. From the perspective of those closely tracking interstellar visitors, this pattern may appear as an intentional distraction, an effort to divert attention away from Atlas's perplexing and potentially groundbreaking characteristics. However, it is more likely that the media's focus on objects with readily observable, visually striking phenomena, like comets that can be seen with the unaided eye, simply reflects the public's and journalists' appetite for easily digestible, spectacular content. Comet Lemon's projected rise to visibility exemplifies this dynamic perfectly. Its expected brightness curve suggests that it will become visible to amateur astronomers around the world, drawing widespread attention due to its accessibility to the general public. In contrast, Atlas remains largely invisible to casual stargazers because it does not produce the immediate, eye-catching visual displays that attract broad media interest. Its scientific significance, though profound, does not lend itself to simple, striking images. Instead, its true mysteries, such as its enormous carbon dioxide coma, its unusual anti-tail behavior, and its unpredictable brightness evolution, demand more complex and technical explanations to be properly understood and appreciated. This necessity for detailed scientific interpretation has contributed to a more cautious approach in communicating Atlas's activity. In recent years, institutions have learned hard lessons about how preliminary findings, if not carefully managed, can be misinterpreted or sensationalized, leading to misconceptions and misinformation. The translation of scientific papers into news headlines often results in a loss of nuance, with uncertainties and complexities getting distorted or omitted altogether. As a result, the careful, measured communication strategy surrounding Atlas may reflect this accumulated weariness, an effort to prevent the spread of misinformation, rather than a specific concern about the object's nature. Adding another layer of complexity, international cooperation among space agencies complicates the timing and coordination of public disclosures. Different national space programs, such as those of Europe, the United States, and others, must balance their respective institutional interests with overarching collaborative scientific goals. The process of aligning announcement schedules to avoid conflicts or overlap is inherently challenging. These logistical hurdles often lead to delays in releasing data or imagery, delays that can be perceived as suspicious or suspiciously convenient by outside observers, especially in an era already rife with speculation and mistrust regarding space phenomena. In summary, the combination of classified observational capabilities, cautious communication practices, and the inherently complex international coordination efforts contributes to a landscape where information about Atlas and similar interstellar objects remains fragmentary and slow to emerge. While these measures are rooted in legitimate scientific caution and operational necessity, their cumulative effect fuels suspicion and conjecture, reinforcing the narrative that significant discoveries are being deliberately withheld from public view. The protocols governing data sharing become especially critical when dealing with cosmic objects like Atlas, which traverse multiple institutional and national boundaries. A fundamental question arises. Which organization holds the primary responsibility for communicating information to the public about such an interstellar visitor? Moreover, how do these institutions coordinate their efforts to ensure that the messaging remains consistent, accurate, and transparent across different teams and agencies? These procedural considerations are not merely bureaucratic, they have tangible impacts on the flow and perception of information that reaches the general public. For decades, public expectations regarding space transparency have been shaped and reinforced by the prolific release of striking imagery from missions such as Voyager, Cassini, and the Mars rovers. These missions established a pattern. Significant space events typically produce a continuous stream of visually compelling images, fostering an assumption that any major discovery should be accompanied by similarly captivating documentation. When such visual evidence is absent, even for scientifically justified technical reasons, it often triggers cognitive dissonance among the public, an uncomfortable sense of inconsistency that conspiracy theories readily exploit. The pattern of selective disclosure observed in government communications, whether about space, national security, public health, or economic policy, further influences how the public interprets gaps or delays in official announcements. These patterns reveal that institutions often prioritize control over the dissemination of information, opting for managed releases that serve strategic or political purposes. Such control mechanisms, especially in scientific publication processes, introduce additional layers of delay before findings reach the public eye. Within professional astronomy, the peer review process is a cornerstone of scientific credibility, but it inherently extends the timeline from discovery to publication. Research findings, no matter how dramatic, must undergo rigorous scrutiny, calibration, and verification, often spanning several months. This means that even when scientists uncover significant anomalies related to objects like Atlas, the initial results remain confined within academic and professional circles until validated and officially published. This delicate dance between scientific caution and public curiosity creates an inherent tension. Scientists aim to understand and accurately interpret anomalies before making definitive claims, while the public desires immediate access to any evidence of cosmic strangeness, regardless of its preliminary status. Reconciling these divergent timelines demands a level of skill, transparency, and communication that institutions are not always adept at providing. As the upcoming Mars flyby approaches, the entrenched patterns of meticulous information management surrounding Atlas have cultivated an atmosphere of suspicion. Any forthcoming release of data will likely be scrutinized not just for what it shows, but equally for what it omits. The perceived element of control, whether justified by scientific prudence or driven by other considerations, has become embedded in the narrative, complicating future efforts at transparency and trust. This dynamic suggests that the challenge of building confidence in the scientific process will persist, especially when publics feel that critical information is being deliberately withheld or filtered. Our first confirmed interstellar visitor, Oumuamua, stands as a remarkable example of scientific transparency and collaborative investigation, a stark contrast to the current silence surrounding Atlas. When Oumuamua was detected, data flowed freely between institutions across the globe, exemplifying an open scientific process that allowed the world to follow every step of discovery in real time. Within days, light curve measurements appeared on preprint servers, enabling researchers worldwide to analyze the object's brightness variations. Shape reconstructions, Rotation period analyses and trajectory refinements were shared promptly, with each new insight openly incorporated into the evolving understanding of this enigmatic visitor. This transparent approach made the entire scientific process visible to anyone interested, fostering a sense of collective discovery and trust. What made Oumuamua's coverage not only possible but also scientifically intriguing was its unusual lack of typical cometary activity. Unlike many objects passing through our solar system, it showed no signs of a coma or tail and no outgassing that could complicate photometric measurements or obscure surface features. This absence of comet-like behavior simplified the observational challenge. Researchers could focus on its shape, brightness, and trajectory without the interference of dust or gas clouds. At the same time, this very lack of activity deepened the mystery surrounding its composition and origin, prompting some to speculate whether it was a natural asteroid, an alien artifact, or something entirely different. The most famous puzzle associated with Oumuamua was the non-gravitational acceleration observed in its trajectory. Unlike purely gravitational paths, this subtle push suggested an unknown force at play. This sparked widespread debate which played out openly in scientific journals and at conferences broadcast to the public. Hypotheses ranged from the idea of a hydrogen iceberg sublimating as it approached the sun, to theories proposing a solar sail driven by solar radiation, or a fragment of nitrogen ice from an alien spacecraft. Each of these explanations prompted follow-up observations and analyses, which were shared openly and collaboratively, allowing the scientific community and an interested public to follow the investigation closely and in real time. Constraints from NASA's Spitzer Space Telescope provided crucial data about Oumuamua's thermal emission, effectively ruling out certain composition models. These null results, published swiftly, demonstrated that negative findings can be as valuable as positive detections in scientific inquiry. They helped refine the hypotheses and narrow down the possibilities, illustrating how transparency and open data sharing foster a more robust understanding. This openness stood in stark contrast to today's situation with Atlas, where spectroscopic observations from the James Webb Space Telescope remain under wraps, and a silence persists despite the object's apparent anomalies. Further analysis of Oumuamua's shape revealed an extreme elongation, suggesting an object unlike any known asteroid or comet. Multiple research teams produced independent papers, each presenting consistent findings that supported the conclusion of a highly unusual geometry. The redundancy of observations, obtained through different instruments and institutions, enabled cross-validation, bolstering public confidence in the scientific conclusions and demonstrating that a transparent, collaborative approach can effectively unravel even the most perplexing cosmic mysteries. The lessons learned from Oumuamua's open investigation are clear. When anomalies trigger immediate public interest, the accumulation of evidence and the presentation of competing hypotheses tend to temper undue speculation rather than inflame it. Transparency in data and analysis fosters understanding, while information gaps tend to breed conspiracy theories and misinformation. Oumuamua's case exemplifies how an open scientific debate can handle extraordinary findings with integrity, reinforcing trust in the scientific process. It's important to note that Oumuamua's lack of cometary activity set it apart from many other interstellar objects. Its absence of a coma or tail meant there were no dust or gas emissions to obscure the object or complicate observations. Without outgassing, there were no pressure effects to unpredictably alter its trajectory, which provided a cleaner, more straightforward dataset for analysis. This clarity made it easier for scientists to develop confident conclusions about its shape, motion, and potential origins. The transparency and openness in investigating Oumuamua not only advanced scientific understanding but also demonstrated the power of collaborative inquiry in the face of cosmic enigmas. The challenges inherent in observing Oumuamua were relatively straightforward, allowing scientists to analyze data swiftly and publish findings in a timely manner. This efficiency was made possible through a model of international collaboration that exemplified the best of astronomy's collective spirit. Teams from various countries shared their observations openly and freely, fostering an environment where different analyses complemented each other, ultimately deepening our overall understanding of this interstellar visitor. Such cooperation maximized the scientific gains from limited observing windows, all while ensuring that public engagement remained a vital part of the investigative process. In stark contrast, the post-August period for Atlas reveals a markedly different pattern of communication. Despite the object exhibiting far more dramatic and unmistakable cometary behaviors that would typically invite active monitoring and prompt sharing, major observatories have been notably reticent. The silence from these institutions raises important questions. Is the complexity of Atlas's characteristics prompting a more cautious, deliberate approach to analysis and disclosure? Or are other factors, perhaps policy decisions, strategic considerations, or technical hurdles, slowing the flow of information? Oumuamua's trajectory took it swiftly away from the inner solar system, creating a sense of urgency that compelled scientists to make rapid decisions about where to allocate observational resources and to publish results quickly. That urgency fostered a dynamic environment where discoveries were swiftly communicated, fueling both scientific progress and public interest. Conversely, Atlas's more measured approach to perihelion, its approach to the Sun, seems to have eased that urgency, allowing scientists to adopt a more slow-paced, deliberate timeline for analysis. While this careful methodology safeguards scientific rigor, it also frustrates the insatiable curiosity of the public eager for real-time updates. Media coverage of Oumuamua offers a compelling case study, illustrating both the advantages and potential pitfalls of transparent science communication. When most outlets accurately conveyed the prevailing scientific uncertainties and presented competing hypotheses with nuance, the public gained a valuable understanding of the investigative process. However, some media sources sensationalized the more speculative explanations, emphasizing the mysterious and the extraordinary, sometimes at the expense of scientific accuracy. This mixed approach to reporting influences how institutions now perceive and manage communication about other anomalous objects like Atlas. From the lessons learned during Oumuamua's investigation, professional astronomers have gained important insights into how to manage public expectations, particularly when dealing with objects that defy conventional understanding. The key is to strike a delicate balance, sharing intriguing discoveries promptly enough to maintain interest, while avoiding premature conclusions that could lead to misinformation or unwarranted speculation. This cautious approach to Atlas may well be a reflection of those lessons, emphasizing thoroughness over speed. The timing of Oumuamua's discovery in October played a crucial role in enabling comprehensive observations. Its appearance allowed scientists to take advantage of optimal viewing conditions, capturing extensive data before the object faded or receded too far away. In contrast, Atlas was discovered in July with its perihelion, the point of closest approach to the Sun, coming in September. This compressed timeline created a much more challenging environment. Limited observational windows, especially as Atlas neared solar conjunction, likely contributed to a more conservative communication strategy, as scientists grappled with the complexities of rapid, high-stakes observation under tight constraints. Yet, an enduring question persists. Why has the level of scientific openness and transparency that characterized Oumuamua's investigation not been mirrored in the study of Atlas? Despite Atlas exhibiting far more dramatic phenomena, such as its extensive coma and unusual tail behavior, public information about its current state has actually become scarcer rather than more abundant. This contrast suggests that factors beyond mere observational difficulty are at play. It hints at the possibility that technical challenges, institutional policies, or strategic decisions are influencing a more restrictive approach to sharing Atlas's data and discoveries. This divergence in communication patterns underscores a broader issue within modern astronomy: the tension between transparency and caution, especially when confronted with phenomena that challenge existing theories. While openness during Oumuamua's passage fostered public understanding and trust, the current reticence surrounding Atlas raises questions about whether scientific caution or institutional discretion is guiding these decisions. The result is a pattern that leaves the public increasingly in the dark about a truly extraordinary celestial visitor, fueling speculation and curiosity about what might be being withheld or simply missed due to cautious protocols. Within a matter of weeks, observatories across the globe verified the remarkable discovery made by Gennady Boris, a detection that confirmed the existence of the second interstellar visitor to our solar system, now famously known as Borisov. Unlike the mysterious and enigmatic object called Oumuamua, which had puzzled scientists with its unusual properties and behaviors, Borisov behaved exactly as astronomers had come to expect from a typical interstellar comet. Its behavior adhered to the well-established patterns predicted by classical comet science, providing a sense of familiarity and reassurance that allowed scientists and the public alike to share in the discovery with confidence. This transparency was so seamless that it felt routine, precisely because Borisov matched the archetype of a conventional comet passing through the inner solar system. As it approached the Sun, its coma, the glowing cloud of gas and dust surrounding its nucleus, evolved in a predictable manner, driven by the solar heat. Spectroscopic observations revealed familiar volatile compounds such as water vapor and carbon monoxide, which outgassed in expected patterns consistent with known cometary physics. The scientific community understood what they were observing, and this clarity fostered a sense of certainty that made them eager to openly share their findings with the wider public. Throughout its journey inward, the Hubble Space Telescope regularly captured images of Borisov, each one consistent with textbook cometary behavior. These images depicted a compact, well-defined nucleus encased in an expanding halo of dust and gas, with a tail stretching away from the Sun under the influence of solar radiation pressure. The visual record, familiar, educational, and reassuring, made it easy for educators and parents to show children clear and relatable images, explaining what a typical comet looks like without encountering any perplexing anomalies or surprises. Major institutions like the European Southern Observatory, NASA, and others maintained a steady flow of official reports and press releases, updating the public on Borisov's evolving characteristics. These updates included estimates of the nucleus's size, details of its chemical composition, and refinements in its trajectory. Adjustments made as gravitational perturbations from planetary bodies subtly altered its course. Each report fit comfortably into existing scientific frameworks, reinforcing the understanding that Borisov was a normal, albeit extraordinary, visitor from interstellar space. Spectroscopic analysis confirmed that Borisov's chemical makeup closely resembled that of comets originating within our own solar system, or the surrounding cloud of icy bodies from which such objects are thought to originate. Its main constituents, water, carbon monoxide, and dust particles, were familiar, validating long-standing theories about planetary formation and the universality of cometary chemistry across different star systems. This close chemical similarity transformed Borisov into a compelling scientific narrative, one that required no caveats or elaborate explanations about unprecedented phenomena. It was, in essence, a straightforward case of an interstellar object behaving like a familiar comet, reinforcing confidence in existing models. When signs of fragmentation appeared in late 2019 and early 2020, the physics involved were well understood. Comets are known to break apart under the stresses of thermal heating and tidal forces exerted by planetary bodies. Such disintegration, while visually spectacular, posed no interpretive dilemmas for scientists. It simply followed the expected physics of icy bodies approaching the sun. The fragments created debris fields that were photogenic and easily documented, making excellent educational material. The process was predictable enough that there was no need for delayed publication or cautious, reserve-laden analysis. Scientists understood what was happening and shared their observations promptly. The key distinction between Borisov and Atlas becomes glaringly evident when comparing their respective trajectories and behaviors. Routine comets like Borisov follow predictable paths and exhibit familiar physical characteristics, which lead to straightforward communication strategies. Public relations that are transparent, consistent, and rapid. In contrast, anomalous objects, like Atlas, generate a series of analytical bottlenecks, forcing institutions to slow their flow of information. When scientists recognize and understand what they are observing, they are comfortable sharing their findings without delay. But when the observed behavior challenges or defies our current models, such as exhibiting unprecedented outgassing, unusual tail structures, or composition, institutional caution naturally increases and the flow of information slows significantly. In the realm of professional astronomy, well-established protocols govern how researchers handle discoveries that deviate from the norm, especially those that demand deeper and more cautious analysis before the findings are made public. When observations align with existing scientific models and are deemed fairly conventional, the peer review process operates efficiently, often producing timely releases that reinforce our collective understanding. However, as the nature of the observation becomes more unusual or complex, pushing the boundaries of current knowledge, the review process inevitably lengthens. Reviewers scrutinize claims more rigorously, demanding higher standards of evidence and clarity, which in turn extends the timeline before any results can be confidently communicated to the public. The case of Borisov exemplifies this pattern. Its behavior conformed closely to what astronomers expect from a typical interstellar comet. Multiple independent observatories tracked its outgassing rates, estimated its nuclear size, and analyzed its chemical composition, each measurement corroborating the others. This redundancy of data created a foundation of confidence, allowing scientists to share preliminary findings with relative ease. The scientific community felt assured because various teams, working with different instruments and methods, arrived at consistent results. This collective verification made it straightforward for press releases to highlight how Borisov's activity mirrored that of local comets, thereby affirming our understanding of planetary formation processes that operate across different stellar systems. Journalists could report on Borisov without needing to wade through complicated technical caveats or grapple with fundamental uncertainties, which made the story both accessible and reassuring. The public engagement around Borisov was satisfying because it reinforced existing knowledge rather than challenging or complicating it. Citizens could follow its journey and learn about comet science through an interstellar object that behaved in familiar, predictable ways, demonstrating the universal physical laws that govern celestial bodies across the cosmos. The narrative was clear, educational, and provided a sense of confidence that our current models of cosmic processes are robust. Furthermore, amateur astronomers played a meaningful role in observing Borisov. Its behavior fell within parameters well understood by the broader community. Backyard telescopes could track its tail development, monitor its brightening curve, and contribute valuable data. activities that amateur observers eagerly undertook and that professional scientists appreciated. This wide participation fostered a collective sense of discovery, deepening public engagement with space science. It made the exploration feel inclusive and transparent, with data coming from a diverse array of sources that reinforced the object's conformity to known cometary behavior. In stark contrast, the coverage of Atlas reveals a different pattern, one marked by careful silence and delays. Unlike Borisov, Atlas exhibits characteristics that are far more difficult to verify independently, and its unusual features complicate efforts to confirm or interpret what is observed. The challenge of communicating about phenomena that do not fit into familiar categories becomes evident. How can scientists explain a carbon dioxide coma extending for half the sun's radius, or interpret an anti-tail that defies basic expectations about solar-wind interactions? These phenomena are far more complex and less intuitive than Borisov's straightforward outgassing, creating a substantial burden on institutions tasked with explaining what might be truly unprecedented behavior. The difficulty lies not only in the phenomena themselves, but also in conveying their significance clearly and accurately to the public, without oversimplifying or misrepresenting the science. The lesson drawn from Borisov's open book approach, one that prioritized transparency and straightforward communication, strongly suggests that when scientific findings are comprehensible, they are more likely to be shared openly and promptly. This transparency fosters public understanding and trust, especially when the phenomena involved are within the realm of familiar, well-characterized physics. Conversely, when observations challenge our existing frameworks and demand intricate explanations, institutions tend to adopt a more cautious stance, resulting in delays, analytical silences, and selective disclosures. Such restraint, while often rooted in scientific prudence, can inadvertently reinforce perceptions of secrecy, skepticism, or even concealment. Overall, Borisov's case demonstrates a fundamental principle. Transparency in space science correlates strongly with the ease of public understanding. When discoveries align with established knowledge, communication flows smoothly, fostering engagement and confidence. When observations are truly anomalous, the complexity and uncertainty require careful, deliberate explanation, often accompanied by delays and silence. Recognizing this pattern is crucial for understanding the dynamics of space exploration communication and the challenges faced when confronting phenomena that stretch the limits of current scientific comprehension. When observations align neatly with our existing scientific frameworks, institutions tend to communicate swiftly and extensively with the public, often sharing detailed images, data, and explanations that reinforce our current understanding of the cosmos. Such transparency fosters trust and curiosity, creating an environment where new discoveries are embraced as natural extensions of established knowledge. However, when data challenges the core assumptions that underpin our understanding of celestial phenomena, particularly the fundamental physics governing interstellar objects, these same institutions tend to revert to cautious, deliberate, and often delayed patterns of analysis and disclosure. This approach, while scientifically prudent, often fuels suspicion and speculation, as the absence of immediate information invites questions about what might be deliberately concealed. This recurring pattern raises difficult and uncomfortable questions. Are the agencies and institutions genuinely withholding complete information because of technical or interpretive difficulties? Or are they selectively sharing data that confirms existing paradigms while quietly suppressing or delaying the release of findings that could threaten those frameworks? In essence, are we witnessing a natural scientific prudence born of caution and rigor, or are we observing a bias, whether conscious or subconscious, favoring discoveries that uphold the status quo over those that could revolutionize our understanding of the universe? Part 8 of this ongoing mystery, How Atlas defies the pattern delves into one of the most astonishing aspects of this interstellar visitor's behavior. The scale of Atlas's carbon dioxide coma is unlike anything ever documented in cometary astronomy. Extending outward from the nucleus for approximately 348,000 kilometers, this gaseous envelope surpasses all known precedents. To grasp the magnitude, consider that this coma spans roughly half the radius of our Sun, a distance greater than most planetary orbits within our solar system. No comet in recorded history has exhibited such an extensive carbon dioxide atmosphere, rendering Atlas a phenomenon without direct comparison, a true anomaly that challenges our most fundamental assumptions. In traditional comet models, the formation of a coma is primarily driven by the sublimation of water ice as an object nears the Sun's warmth. Carbon dioxide, when present, usually plays a secondary role, contributing to comparatively modest atmospheric layers that expand only slightly beyond the nucleus. Atlas, however, appears to invert this hierarchy entirely. Here, CO2 dominates the outgassing process, creating an atmosphere so vast that it defies conventional expectations regarding comet composition and behavior. Such a chemical profile compels us to reevaluate core principles about how interstellar objects form, evolve, and interact with solar radiation. Further perplexing is the documented sunward plume observed in both Hubble and Gemini imagery. This feature directly violates the basic physics outlined in standard cometary science. Normally, solar wind pressure and radiation push material away from the Sun, forming the characteristic tail-pointing anti-sunward, that is, away from the star. Instead, Atlas exhibits a striking anti-tail, an intense stream of material pointing directly toward the Sun, as if defying the fundamental forces that govern all other comets studied to date. This anti-tail phenomenon suggests that the dust grains involved might possess characteristics unlike anything in our experience. Perhaps the particles are so massive that solar radiation pressure cannot dislodge or accelerate them, or electromagnetic forces could be interacting with charged particles in ways our current models do not account for. It's also possible that the rotation of Atlas itself creates jets that launch material in directions seemingly at odds with known physical law. Each of these explanations requires assumptions that stretch or even break the boundaries of established cometary science, pointing to phenomena that are fundamentally anomalous. Adding to the enigma, reports in mid-September indicated rapid brightening, an unexpected shift in Atlas's luminosity profile. Amateur astronomers diligently tracking the object from their backyard telescopes observed magnitude increases that significantly exceeded the predictions derived from our current models. Some observers claimed that Atlas had brightened by as much as 20 times beyond expected levels, a staggering discrepancy that, if confirmed, would imply internal processes or behaviors far beyond conventional understanding. While these estimates remain unverified through professional analysis, the sheer magnitude of the claimed increase deepens the mystery, suggesting that Atlas might harbor volatile or energetic phenomena that defy our current scientific frameworks. Throughout this unfolding story, each new anomaly, be it the immense carbon dioxide coma, the anti-tail behavior, or the rapid brightening, only amplifies the sense that Atlas represents a new class of celestial object, one that could fundamentally alter how we perceive interstellar visitors. Yet the reluctance or delay in providing comprehensive verified data leaves us with unanswered questions and growing suspicion. Are these delays due to the inherent complexity of analyzing such an extraordinary object, or do they hint at a deeper, more troubling reality, that some aspects of Atlas's nature are being deliberately kept from public view? Discrepancies in observational data might simply stem from measurement errors, instrumental variances, or differences in observational techniques, factors that are common in complex scientific endeavors rather than indicators of genuine anomalies. However, what if these brightness reports are accurate? A comet exhibiting a 20-fold increase in luminosity beyond what our models forecast would imply that processes within or surrounding its nucleus are operating in ways we cannot currently explain. Perhaps the sublimation rates, how quickly volatile materials turn from solid to gas, are accelerating beyond the expected thermal curves, suggesting an internal energy source or a chain reaction triggered by solar heating. Alternatively, the internal structure of the object might be exposing new volatile-rich layers that were previously hidden. Or the object could be undergoing fragmentation, breaking apart into smaller pieces that collectively increase its surface area and, consequently, its brightness. Adding to this growing mystery is the observed shift in color during late August and early September. Photographers and astronomers began noticing a distinct greenish tint in Atlas's coma, a luminous cloud of gas and dust surrounding the nucleus, likely caused by excited molecules such as decarbon or cyanide compounds energized by solar radiation. These chemicals are common in comets, but their pronounced presence in Atlas suggests either an unusual abundance or an enhanced excitation mechanism that amplifies their visibility. The tentative nature of the green coloration's identification underscores another troubling aspect of the investigation. Despite visual observations and photographic evidence indicating specific chemical signatures, definitive spectroscopic confirmation, analyzing the light to precisely identify chemical compositions, remains conspicuously absent from official releases. Multiple observatories equipped with the necessary spectroscopic instruments have the capability to verify these chemical signatures, yet official channels have not provided conclusive data. Meanwhile, Atlas's trajectory through the inner solar system appears almost meticulously choreographed to allow maximum observational opportunities. Its upcoming close approach to Mars on October 3rd positions multiple spacecraft orbiting the red planet for unprecedented, detailed, close-range observations, an event that could yield invaluable insights into its structure and composition. Furthermore, the perihelion, the point at which Atlas will be closest to the Sun, arrives in late October at distances where solar heating should provoke clear and significant changes in its physical state, providing an ideal window to study how such objects evolve under intense solar influence. The alignment of this approach with Earth-based observation windows seems no coincidence. It appears deliberately calibrated to maximize scientific return. While some skeptics see this as more than mere coincidence, orbital mechanics, gravitational interactions within the three-body system of Atlas, the Sun, and the planets, can naturally produce surprising and seemingly intentional alignments that enhance our ability to observe and analyze. Managing public expectations becomes especially critical when dealing with objects exhibiting behaviors as anomalous as Atlas. Humanity's collective consciousness has become accustomed to regular releases of space imagery, standardized snapshots and data from missions that systematically document our cosmic neighborhood. As Atlas's strange and unprecedented behavior intensifies, the decreasing flow of imagery and data creates a cognitive dissonance, fueling speculation and conspiracy theories about deliberate concealment. The gap between the object's growing oddities and the dwindling amount of publicly available visual documentation feeds fears that something is being hidden. Meanwhile, scientific analysis pipelines, complex procedures involving peer review, data calibration, and validation, tend to slow down when confronted with data that defies existing categories and models. Peer reviewers require additional time to scrutinize claims that challenge established understanding, especially when the evidence suggests phenomena that are difficult to explain within current scientific frameworks. The process of scientific validation becomes considerably more rigorous when a discovery challenges existing paradigms. Scientific journals, especially those handling groundbreaking phenomena, demand meticulous verification before any findings are disseminated to the public. The more extraordinary the claims, such as reports of a celestial object that seemingly defies the fundamental principles of cometary physics, the more extensive and prolonged the peer review becomes. This inevitably results in delays, sometimes stretching over months, before any official communication reaches the wider audience. Such cautious scrutiny is essential to uphold scientific integrity, but it also places a heavy burden on the institutions responsible for the analysis and dissemination of data. These organizations may feel unprepared for the intricate complexity of phenomena like Atlas, which appears to challenge multiple facets of conventional cometary science. Its unprecedented size, composition, and anomalous behaviors. Communicating about an object that seemingly breaches the foundational laws of astrophysics presents a profound challenge. How does one explain a celestial body that appears to operate outside the bounds of established understanding? How can scientific credibility be maintained while openly acknowledging the deep uncertainties that surround these observations? The task of translating such anomalies into accessible, accurate explanations may be beyond the current communication frameworks that space agencies typically rely upon. These organizations are accustomed to sharing well-understood data, images of familiar celestial phenomena, standard spectroscopic findings, and predictable behaviors. But when confronted with something that appears to violate the very principles of cometary physics, traditional communication channels may fall short, risking either misinterpretation or unwarranted skepticism. At an international level, the complexity multiplies. Different agencies and institutions, each with their own protocols, priorities, and interpretative frameworks, may arrive at contrasting conclusions about the same data. For instance, while NASA might interpret Atlas's unusual features as potential signs of artificial origin, the European Space Agency or other partners might view the same observations as extraordinary but explainable within the bounds of natural phenomena. These divergent perspectives can lead to conflicts that require diplomatic negotiation and careful coordination before any findings are publicly released. The goal of collaborative science is to present unified, credible information, but reconciling differing institutional interests and analytical conclusions adds a layer of difficulty that can further delay transparency. The timing of Atlas's closest approaches to Earth and Mars compounds these challenges. These events, such as the upcoming flyby near Mars and the perihelion passage, are precisely when public interest and curiosity are at their peak. Ironically, these periods often coincide with observational difficulties, notably due to solar conjunction, when the object's position relative to the Sun renders Earth-based observations unreliable or impossible. As the object approaches perihelion, solar radiation and interference make direct observation from ground telescopes more challenging, limiting the ability to gather new, definitive data exactly when public fascination is most intense. This creates a perfect storm. High curiosity driven by anticipation of groundbreaking revelations, combined with technical limitations that restrict observations. During these blackout periods, speculation about what might be hidden or what revolutionary phenomena could be occurring naturally intensifies. The implications are significant. If Atlas's peculiar traits indeed stem from new physics or advanced extraterrestrial technology, then the delay in gathering and communicating confirmatory evidence could hinder timely scientific understanding. Such an event would warrant careful, deliberate analysis, potentially requiring extended periods of scrutiny to avoid premature claims that could mislead or cause unwarranted alarm. However, past experiences with interstellar visitors like Oumuamua and Borisov suggest that transparency and real-time scientific debate serve to strengthen public trust. When Oumuamua's non-gravitational acceleration was openly discussed and analyzed by the scientific community, It not only clarified the nature of the phenomenon, but also demonstrated an honest, rigorous process of investigation, one that embraced uncertainties rather than obscured them. Similarly, Borisov's behavior aligned well with conventional comet science, and its data were shared openly and promptly, reinforcing confidence in the scientific method. In contrast, Atlas's current approach, marked by a notable silence from major observatories and agencies, represents a departure from this precedent of transparency. The core question centers on whether this silence is a necessary reflection of cautious scientific practice or a manifestation of institutional fear. Fear that revelations might challenge accepted worldviews or provoke public unrest. Either scenario carries profound implications. If the former, then a deliberate, careful approach safeguards scientific credibility. If the latter, it risks eroding public trust and fostering suspicion about what is being concealed. The future of space exploration and discovery hinges on this balance. Transparent, real-time investigation not only fosters understanding but also nurtures public confidence and engagement. Conversely, excessive secrecy, especially concerning phenomena that could revolutionize our understanding of the universe, may breed skepticism and conspiracy theories, ultimately undermining the very foundation of scientific progress. As the community stands on the cusp of potentially transformative revelations, the manner in which Atlas is studied and communicated will serve as a defining example of how humanity navigates the delicate interface between curiosity, caution, and trust. The distraction theory. As September unfolded, a subtle yet intriguing shift became apparent in the realm of astronomical headlines, a shift that keen observers of space media could not ignore. During the period when Atlas was approaching its most scientifically significant phase, the close Mars flyby and subsequent perihelion, public focus seemed to be deliberately steered away from this enigmatic interstellar visitor. Instead, the spotlight was systematically cast upon other celestial objects that offered more familiar, straightforward, and visually captivating cosmic spectacles. Objects that could be appreciated with minimal technical knowledge and without the need for complex interpretation. One prime example of this redirection was the dramatic fragmentation of Comet Swan in early September. The event provided exactly the kind of vivid, photogenic spectacle that space journalism and media outlets often favor. The comet visibly disintegrated in real time, scattering debris across space and forming tail structures that evolved rapidly. An unfolding cosmic drama easily captured by amateur astronomers using backyard telescopes. These images of Swan's destruction flooded social media and astronomy forums, and the event was repeatedly featured on NASA's Astronomy Picture of the Day, which showcased multiple images of the comet's breakup. The imagery depicted a classic case of cometary disintegration, behaving precisely in accordance with textbook physics, an outcome that reassured viewers that they were witnessing a natural, predictable cosmic process. The timing of this spectacle seemed far too convenient for those seeking to divert attention from Atlas. Just as questions about the interstellar visitor's unusual and perplexing behavior, its unexpected brightness changes, anti-tail phenomena, and anomalous coma were reaching a crescendo, Swan's spectacular demise offered a compelling distraction. It required no elaborate explanation, no acknowledgement of scientific uncertainties, and no complex interpretation. Citizens could simply observe a comet dying in a manner that was both comprehensible and familiar, an event that fit neatly into a narrative of natural cosmic processes, rather than puzzling over the strange, unprecedented features of Atlas's behavior. Similarly, Comet Lemon emerged in September as another convenient focal point for astronomical interest. Predictions indicated that Lemon might brighten significantly, potentially reaching a magnitude between 2 and 4 by late October, making it visible to the naked eye for observers around the world. Media outlets naturally gravitated toward such phenomena as they offer relatable and visually accessible spectacles. Unlike Atlas, whose detailed and often perplexing imagery remained largely confined to professional observatories and scientific analyses, Lemon promised an opportunity for amateurs and the general public to witness a comet's journey firsthand. This emphasis on Lemon's visibility created a compelling narrative of accessible astronomy, one that contrasted sharply with Atlas's complex technical nature. While Atlas remained an abstract, often opaque subject, supported chiefly by sophisticated imagery and spectroscopic data that could only be interpreted by specialists, Lemon presented a tangible, immediate opportunity for ordinary citizens to step outside, look up, and potentially see a bright comet with their own eyes. The implication was clear. The public could participate directly in cosmic discovery, observing a familiar comet rather than being left to puzzle over a mysterious interstellar object that required specialized equipment and expert interpretation. The appeal of participatory astronomy versus passive consumption of scientific analysis was unmistakable. Publications like Star Walk, Sky and Telescope, and other astronomy outlets quickly shifted their October coverage to highlight Lemon's expected performance. They published viewing guides, sky charts, and photography tips, flooding online communities with resources designed to help amateurs find and photograph Lemon. This surge fostered a sense of anticipation and excitement around an object promising conventional cometary behavior. Brightening, tail development, and easy visibility, elements that the average person could relate to and enjoy. Meanwhile, the implicit message conveyed was that people should focus on the celestial object they could see with their own eyes, rather than worry about the one that remained largely an abstract technical mystery. Atlas. The message was straightforward. Look here, see this, and understand it. Don't bother with that complex, enigmatic visitor. This deliberate redirection of attention was not necessarily a conscious editorial decision, nor did it have to involve any overt conspiracy. Whether driven by media habits, editorial preferences, or natural tendencies to favor more accessible stories, the effect was the same. Public interest was guided away from Atlas's perplexing behavior toward more familiar and less challenging celestial phenomena. In the end, whether this shift in focus was a product of deliberate editorial coordination or an organic response to audience preferences remains uncertain. What is clear, however, is that the effect was undeniable. By highlighting more conventional comets like Swan and Lemon, the media and astronomy communities effectively created a narrative landscape where the mysterious, complex behavior of Atlas was pushed to the background, making space for easily digestible, relatable cosmic spectacles. Spectacles that required no deep scientific understanding and offered immediate visual gratification. Public attention shifted away from Atlas precisely at the moment when its most intriguing features were beginning to unfold. This pattern of media coverage can be explained through rational psychological factors that do not necessarily involve any conspiracy. Journalists tend to favor stories that their audiences can connect with directly, those that evoke personal experience rather than complex scientific mysteries that demand deep technical understanding. Bright comets visible to the naked eye, for example, naturally generate more interest because they allow people to witness the phenomena firsthand, creating a sense of direct participation. In contrast, telescopic objects or phenomena requiring specialized equipment tend to generate less engagement because they rely on vicarious learning, trusting experts to interpret data rather than offering an immediate visceral experience. The commercial model of astronomical journalism further reinforces this trend. Content that is accessible to amateur astronomers, such as bright comets within reach of backyard telescopes, tends to attract more social media shares, website traffic, and overall reader attention than reports about objects that demand sophisticated understanding or technical background. Media outlets responding instinctively to audience metrics are more likely to emphasize stories about objects like lemon, whose visibility and simplicity make them more appealing, over more mysterious or complex phenomena like Atlas, regardless of any underlying editorial intent. Educational institutions also operate under similar incentives. When designing outreach programs, planetariums, universities, and science museums find greater value in showcasing phenomena that visitors can observe directly or easily understand. Simply put, a comet that can be seen with modest equipment is more effective in engaging the public than an enigmatic interstellar visitor whose behavior and characteristics require specialized knowledge to interpret. This makes Atlas less suited for general education compared to more straightforward objects like lemon. However, the timing of this shift in attention feels suspiciously convenient for those seeking to minimize focus on Atlas's bizarre and potentially revolutionary behavior. Just as its unprecedented features, such as its unusual coma and anti-tail, began raising uncomfortable questions about gaps in scientific understanding, alternative cometary phenomena quickly emerged to divert curiosity away from Atlas. During September, professional astronomy conferences exhibited a similar pattern. Presentations about Swan's fragmentation or Lemon's brightening far outnumbered discussions about Atlas, despite the far greater scientific significance of the interstellar object. Whether this prioritization reflected genuine research interests or deliberate strategic communication remained unclear to outside observers. Social media algorithms played a significant role in reinforcing this attention shift. While it might appear that these shifts were orchestrated, they were largely driven by automated engagement optimization. Content focusing on visible comets, images, brightening reports, or fragmentation tended to garner far more shares, comments, and views than technical discussions involving spectroscopic analysis or the physics of anti-tails. These platform algorithms naturally promoted content that elicited higher user engagement, thereby creating an artificial emphasis on accessible astronomy that often overshadowed the object's true scientific importance. During this period, the European Space Agency's communication strategy also leaned heavily toward other missions. Instead of emphasizing Atlas updates, ESA prioritized announcements related to Mars exploration achievements, remote galactic surveys from the Webb telescope, and results from the Gaia spacecraft, topics that, while important, diverted public and media focus away from the interstellar visitor. Meanwhile, their Mars orbiters prepared for what could be one of the most significant encounters in human history, an opportunity to observe Atlas up close. Yet official updates on this mission remained limited. This pattern of shifting attention and selective emphasis underscores how strategic communication and media dynamics can shape public perception, often in ways that mask the full scope of scientific investigation surrounding Atlas. The apparent disconnect between the activities of preparation and the priorities of public communication appeared starkly misaligned, revealing a complex interplay of strategic choices. Within the amateur astronomy community, this divergence became evident through noticeable splits in their discussions during September. Some online forums and observation groups remained intensely focused on tracking Atlas, sharing imaging attempts and analyzing its behavior, reflecting a dedicated scientific curiosity. Meanwhile, other segments of the community shifted their attention toward the preparation and documentation of Comet Lemon and the detailed observation of the Swan fragmentation, which provided visually dramatic and easily digestible content. This division might mirror differing community priorities, those driven by scientific investigation versus those motivated by aesthetic appreciation or entertainment. Yet it also served to diffuse the concentrated attention Atlas had commanded during its peak visibility in August. This phenomenon, the dispersal of focus, resonates with the long-standing distraction theory, which finds credibility when viewed in the context of historical precedents for managing public attention during sensitive or potentially controversial discoveries. Governments and space agencies have repeatedly employed strategic timing to influence media coverage, often scheduling announcements or releasing information to coincide with other major news events capable of absorbing the public's and media's focus. While space agencies generally operate with a higher degree of transparency than many other institutions, they are not immune to the same pressures to shape public reaction, especially when discoveries could cause confusion, concern, or destabilize certain narratives. Whether these shifts in coverage were deliberate distractions or simply natural evolutions within the media landscape, the effect was the same: a significant reduction in public scrutiny during what many consider to be Atlas's most scientifically critical phase. As the object drew nearer to Mars, experienced perihelion heating, and potentially revealed aspects of its true nature, the global attention that might have been expected to intensify was instead diverted elsewhere. Meanwhile, the focus of the public and media was drawn to other celestial phenomena, or general space news, effectively silencing the broader discourse around Atlas's enigmatic behaviors. This timing naturally raises important questions about whether this pattern of coverage will persist in future encounters with similarly anomalous interstellar visitors. Will we see a repeat of this strategic shifting of attention during subsequent close approaches or perihelion passages? Or is this a reflection of an underlying systemic approach to managing cosmic discoveries, one that prioritizes control over full transparency when faced with objects exhibiting extraordinary or potentially disruptive features? Part 10. The Don't Look Up Scenario. The 2021 film Don't Look Up, produced by Netflix, encapsulated a deep-seated societal fear that has lingered in the collective consciousness for decades. What if those in positions of power deliberately choose to conceal cosmic truths to prevent societal chaos? The movie's core premise, that authorities might downplay or even hide the existence of a genuine asteroid threat to avoid economic collapse, political upheaval, or widespread panic, resonates with many real-world observations of how institutions often manage information during crises. These actions are sometimes motivated by a desire to maintain stability, prevent mass hysteria, or avoid triggering economic fallout. Though fictional, Don't Look Up offers a powerful conceptual framework for contemplating how genuine cosmic discoveries could be handled when they challenge our most comfortable assumptions about our place in the universe. Applying this lens to Atlas should be viewed as a thought experiment, not an accusation. Importantly, the object itself poses no immediate threat to Earth. NASA's trajectory calculations confirm that the closest approach in December will occur at a distance of approximately 1.8 astronomical units, far beyond any collision risk. Yet the question arises, what if Atlas represented a different kind of threat? Not a physical one, but a profound challenge to our understanding of reality. Consider the psychological impact if Atlas's characteristics suggested some form of artificial origin or technological enhancement rather than a natural interstellar visitor. The anti-tail behavior, an unusual phenomenon where the tail points directly toward the sun, could hint at propulsion systems operating beyond our current scientific comprehension. Similarly, the unprecedented scale of its carbon dioxide coma might suggest controlled outgassing for navigational or energy purposes, rather than passive sublimation typical of comets. If Atlas were indeed an engineered object, its behaviors and features could signify technological capabilities that radically alter our understanding of what is possible beyond our solar system. Such revelations, if publicly disclosed, might induce widespread cognitive dissonance, existential anxiety, or societal upheaval. The potential for these discoveries to challenge deeply held beliefs about humanity's uniqueness or the nature of the universe might motivate those in charge to manage the information carefully, perhaps even to conceal or delay full disclosure until a more controlled, staged release could be orchestrated. In this hypothetical scenario, the Don't Look Up framework underscores the importance of considering how the management of cosmic truths, whether through deliberate concealment or strategic timing, can influence societal stability. It prompts us to reflect on whether the current silence surrounding Atlas's true nature is driven by genuine scientific caution, geopolitical considerations, or a more calculated effort to control the narrative about our cosmic environment. The carefully plotted course that maximizes observational opportunities might in fact be a deliberate adjustment rather than a mere consequence of natural orbital mechanics. Such precise trajectory modifications could suggest intentional course corrections aimed at facilitating specific observations, rather than random or purely gravitational influences guiding its path. It's important to note that these are purely speculative notions. None of these ideas are backed by confirmed data. Instead, they are extrapolations based on patterns of anomalous behavior that, while unusual, could potentially be explained through natural phenomena with further understanding. But suppose space agencies did have concrete evidence indicating that Atlas exhibits artificial, possibly extraterrestrial characteristics. In such a scenario, would immediate public disclosure truly serve the greater good? Revealing that we are being visited by technology beyond our current comprehension could cause significant social upheaval, fear, or chaos. In this context, temporary secrecy might be justified, providing time for experts to develop appropriate frameworks for explaining and contextualizing such extraordinary findings, minimizing panic while preparing the public for the eventual revelation. Looking at history, institutions have tended to approach revolutionary discoveries with caution rather than full transparency. This pattern is evident in the long delay between initial military encounters with unidentified aerial phenomena, UAP, and their eventual acknowledgement by the public. These instances demonstrate how national security concerns often override the impulse for open scientific communication, especially when the phenomena observed resist conventional explanations and threaten to challenge existing worldviews. The implications extend beyond security. The economic impact of confirming the existence of advanced extraterrestrial technologies could be profound. Such confirmation might destabilize markets, currencies, and entire sectors of industry, particularly if it becomes evident that these visitors possess propulsion or engineering capabilities far beyond human technology. For example, if Atlas demonstrated propulsion methods that rendered current transportation or energy systems obsolete, the resulting economic upheaval could dwarf the scientific significance of the discovery itself. Additionally, the potential for religious and philosophical upheaval cannot be ignored. Many foundational worldviews depend on humanity's perceived uniqueness or central role within the universe. Evidence of civilizations capable of traversing the galaxy might force societies to reevaluate their beliefs, possibly leading to social fragmentation, existential crises, or widespread uncertainty. Governments and institutions might feel compelled to manage public opinion carefully, preparing populations gradually to accept such paradigm-shifting revelations. The Don't Look Up scenario encapsulates a hypothetical situation where authorities hold concrete evidence of extraordinary phenomena, but opt to conceal it from the public. In reality, the situation with Atlas is more likely characterized by genuine uncertainty. Scientists and analysts are probably grappling with the challenge of distinguishing between unknown natural processes and potential artificial origins, and prematurely releasing unverified or ambiguous data would be scientifically irresponsible. Political considerations further complicate any effort to maintain secrecy. Multiple space agencies and research institutions around the world are studying Atlas independently. making coordinated concealment exceedingly difficult without clear evidence of deliberate suppression. Achieving consistent information management across different nations, each with its own political agendas, protocols, and levels of transparency, would require an unprecedented level of international cooperation, something that is highly unlikely in the current geopolitical climate. Even amateur astronomy presents challenges to systematic concealment. With a global network of citizen scientists and hobbyists equipped with increasingly sophisticated instruments, the likelihood of suppressing all observations becomes even more remote. Independent observers, from backyard astronomers to university-affiliated research groups, can capture and analyze data on Atlas, making it nearly impossible to control or hide all potential sources of information. Amateur astronomers, working from their backyards and equipped with increasingly advanced tools, are now capable of independently detecting and analyzing cosmic phenomena. This widespread global network of dedicated hobbyists creates a layered and redundant system of observation that makes it nearly impossible for any organization, whether governmental or institutional, to completely suppress knowledge of anomalous discoveries over a sustained period. In the era of the Internet, the dynamics of controlling information have fundamentally shifted from what they were in previous decades, when authorities could more easily gatekeep and restrict access to sensitive or extraordinary data. Today, social media platforms, online forums, and international communication networks facilitate multiple channels for sharing information that bypass traditional authority structures, allowing independent voices and collective efforts to flourish beyond official control. However, despite these democratic channels of dissemination, the strategic and selective release of information remains feasible even in societies that pride themselves on transparency. Authorities or scientific organizations can time announcements carefully, aiming to minimize public attention, while emphasizing more conventional explanations and downplaying or omitting details that might highlight anomalies. They might also steer media coverage toward other more familiar topics, thus shaping public perception and understanding without resorting to outright deception. This raises a compelling question. If a scenario similar to the fictional "Don't Look Up" were unfolding in reality, where crucial information is being withheld or delayed, would we recognize it when it happens? The conspicuous absence of dramatic, detailed public disclosures about Atlas's true nature could be interpreted in two ways. It might simply reflect routine scientific caution, where experts prefer to proceed carefully to avoid spreading misinformation or causing unnecessary panic. Alternatively, it could be a deliberate form of information management designed to prevent social disruption or confusion. Distinguishing between these possibilities remains challenging, as the internal decision-making processes behind such choices are often opaque to outside observers. The message conveyed by the film "Don't Look Up" ultimately suggests that truth tends to surface eventually, regardless of attempts at concealment, but by the time it does, it may be too late to effectively serve the public good or foster meaningful engagement. If Atlas truly signifies a paradigm shift, challenging our existing understanding of interstellar visitors, then delaying the disclosure of its true nature might sacrifice critical opportunities for productive public engagement and democratic participation. Humanity's collective response to such an extraordinary discovery depends on timely, transparent communication. The psychological power of the "Don't Look Up" narrative lies in its recognition that authorities often prioritize societal stability over full transparency when faced with information that could threaten the established order. While it remains speculative whether this dynamic is actively at play around Atlas, the pattern of reduced transparency during its most intriguing phases certainly provides fertile ground for such concerns to grow within the public imagination. Currently orbiting Jupiter in a highly elongated elliptical trajectory, The Juno spacecraft was deliberately designed to probe the depths of the gas giant's atmospheric dynamics and interior structure. Its path is optimized for studying the complex interactions within Jupiter's atmosphere, not for intercepting distant objects like Atlas. To redirect Juno toward an intercept course with Atlas would require a monumental change in its velocity, a maneuver scientists refer to as a delta V boost, an engine burn powerful enough to significantly alter the spacecraft's trajectory. Such a maneuver would demand an immense amount of fuel, far beyond what Juno currently has on board. Detailed technical evaluations, including discussions on platforms like Space Exploration Stack Exchange, paint a stark picture of the formidable engineering hurdles involved. In essence, for Juno to reach Atlas, it would need to escape Jupiter's gravitational hold, modify its course precisely to align with the comet's trajectory, and execute a timed burn to ensure an intercept during Atlas's upcoming Jupiter flyby, scheduled for March of 2026. However, the energy required for such a maneuver is likely impossible to fulfill with Juno's remaining fuel reserves, rendering the mission concept infeasible given current technological and resource constraints. Yet amidst these technical realities, an even more compelling aspect of the discussion has emerged, one that reveals a broader attitude about how space agencies approach potential discoveries. The assumption that NASA would, under ideal circumstances, pursue a close-up investigation of Atlas seems almost automatic. Many media outlets and opinion pieces have championed the idea that retargeting Juno for this purpose would be the obvious logical choice. This expectation has been framed as a matter of course, prompting questions about why NASA has not already announced plans to do so. This absence of official intent has begun to raise eyebrows among observers who anticipate a more aggressive scientific pursuit of extraordinary phenomena. Notable astrophysicist and Harvard professor Avi Loeb has become a prominent voice advocating for more proactive measures, calling for dedicated spacecraft missions to study Atlas in detail. In articles published in outlets like the Boston Herald, Loeb argued that humanity is missing an unprecedented opportunity to examine an interstellar visitor that might hold the key to understanding planetary formation processes in other star systems, or perhaps even more exotic, unknown phenomena. His advocacy suggests that the potential scientific gains are too significant to ignore. However, pushback from mission planning experts underscores the conservative nature of space agency decisions. Launching or redirecting spacecraft involves years of meticulous planning, rigorous technical reviews, and enormous financial investments. Redirecting existing missions toward targets like Atlas, especially on short notice, entails risks that could jeopardize the primary objectives of those missions. For example, other spacecraft with less dramatic but still valuable observational potential are currently en route to different targets, such as NASA's Psyche mission, which is headed toward a metal-rich asteroid, or ESA's JUICE spacecraft, which is traveling to study Jupiter's icy moons. Depending on their trajectory timing, these missions might be able to achieve distant observations of Atlas, but such opportunities lack the excitement and immediacy of a close intercept. Still, they could yield meaningful scientific data, even if only in the form of remote sensing. Furthermore, the Parker Solar Probe presents perhaps the most intriguing possibility of all. Equipped with a wide-field imaging instrument called the Wide Field Imager for Solar Probe, it could potentially capture valuable data on Atlas during the comet's perihelion, the closest approach to the Sun, in late October or early November. Although primarily designed to study solar phenomena, this spacecraft's trajectory and instrumentation might incidentally record Atlas's behavior as it passes through the inner solar system, offering a unique vantage point that complements ground-based and other space-based observations. Despite the technical and logistical challenges, the core of the discussion reveals a fundamental expectation. that humanity's exploration agencies driven by scientific curiosity would seize every opportunity to investigate anomalies like Atlas up close, if it were within reach. The silence or lack of overt pursuit in this case hints at the complexities and cautious conservatism that govern space exploration decision-making. Still, the debate underscores a broader question. How far are we willing to go and how quickly when extraordinary cosmic visitors appear? The strategic positioning of spacecraft near the Sun offers a rare and potentially invaluable vantage point from which to observe Atlas's peculiar anti-tail behavior and the evolution of its coma during the intense phase of solar heating. Such observations could shed light on the physical processes driving its unusual dynamics, especially as the object approaches perihelion. Despite the scientific significance, public discourse surrounding these opportunities remained surprisingly sparse, especially when contrasted with the considerable attention given to more conspicuous intercept scenarios, those dramatic close approaches or potential contact missions that often capture the imagination. This preference for direct close-up investigation stems from a common misconception about how astronomical discovery typically unfolds. In reality, understanding complex cosmic phenomena generally relies on a methodical process of patient, multi-perspective observation. It involves collecting data over time from various vantage points, rather than relying on a single decisive encounter that might provide an immediate, spectacular image. This approach allows scientists to piece together a comprehensive picture of the object's behavior and internal structure, minimizing the risk of misinterpretation caused by transient or misleading features. Adding to the intrigue is the conspicuous absence of publicly announced spacecraft missions explicitly targeting Atlas. This silence has fueled speculation about underlying policy decisions, whether certain operations are being deliberately concealed or classified. If the object displayed signs that strongly suggested artificial origins or extraterrestrial technology, one might expect military or intelligence agencies to deploy space-based sensors capable of closer, more detailed examination. Their silence, therefore, raises questions. Does it indicate that no concerning or extraordinary discoveries have been made? Or alternatively, that covert investigations are already underway and being carefully hidden from public view? Another layer of complexity involves the role of commercial space capabilities. In recent years, private companies have grown increasingly capable of supporting rapid response missions, possessing spacecraft and launch systems that could potentially investigate objects like Atlas at relatively low cost. Yet, surprisingly, there has been little mainstream attention on this front. The lack of announced commercial initiatives may reflect economic considerations. Companies might be weighing the costs and risks of such missions against their potential scientific or commercial benefits. Alternatively, it might suggest that private enterprise is simply not yet engaged in this specific arena, possibly due to perceived uncertainties or regulatory hurdles. International space agencies' responses have also been uneven. While the European Space Agency has made public its intention to observe Atlas during the October flyby with Mars orbiters, many other national programs have remained notably silent about their own investigation plans. These disparities could be rooted in differing scientific priorities, resource allocations, or levels of concern regarding Atlas's anomalous characteristics. For instance, China's space program, which has demonstrated significant advancements in recent years, has not publicly disclosed any specific plans to study Atlas. Yet given China's capabilities, possessing advanced spacecraft and launch technology, they have the means to support targeted interstellar object studies. Their silence, however, continues to fuel speculation among observers familiar with their growing space ambitions. Additionally, amateur astronomers and university-led research initiatives represent largely untapped resources for investigating Atlas. Student-built CubeSats and privately funded space missions could, in principle, contribute valuable observations, especially at lower costs, complementing the efforts of larger agencies. These smaller, agile platforms have the potential to provide continuous monitoring or targeted imaging that might be more flexible than traditional government programs. Unfortunately, coordination with these communities appears limited, perhaps due to logistical, regulatory, or institutional barriers. This situation prompts a fundamental question. Are humanity's efforts to investigate our third confirmed interstellar visitor truly maximized? Or are institutional caution and risk aversion preventing us from seizing a potentially unprecedented scientific opportunity? In the face of a mysterious object that challenges our understanding of natural and artificial phenomena, the limited scope of current initiatives raises doubts about whether we are doing everything possible to gather crucial data that could fundamentally alter our understanding of interstellar objects and the broader cosmos. The growing disparity between public expectations for vigorous scientific scrutiny and the apparent hesitance or reluctance of institutional agencies to pursue such investigations hints at underlying issues, either hidden constraints or deliberate policy decisions, that serve to limit our collective cosmic curiosity. As Atlas drew nearer to its closest approaches to both Mars and the Sun, the conspicuous absence of dedicated spacecraft missions to study it firsthand began to feel like a missed opportunity of unprecedented historical importance. Whether this shortfall stemmed from resource limitations, prioritization of other scientific agendas, or perhaps a troubling institutional blindness to the broader significance of such interstellar visitors remains an open question, one that future encounters with interstellar objects may hopefully help clarify. Now, approaching the critical moment, the upcoming Mars flyby, scheduled for October 3, 2025, stands out as humanity's most promising chance to obtain definitive high-resolution imagery of Atlas since the mysterious drought of telescope releases that began in August. On that precise date, this enigmatic interstellar traveler will glide within approximately 30 million kilometers of Mars, roughly 19 to 20 hundredths of an astronomical unit, placing it within reach of multiple orbiting spacecraft capable of unprecedented close-range observations. The European Space Agency has already confirmed its intention to deploy observational efforts during this window, utilizing their Mars Express orbiter and the ExoMars Trace Gas orbiter, both of which are sophisticated spacecraft equipped with high-resolution imaging instruments and spectroscopic tools, capable of revealing detailed chemical and morphological features. NASA's Mars Reconnaissance Orbiter, renowned for its powerful high-resolution imaging science experiment, HiRISE camera system, could potentially join the campaign contingent upon the specific orbital geometry at the time of flyby, maximizing the opportunity for detailed observation. Additionally, the Mars Atmosphere and Volatile Evolution, MAVEN spacecraft, primarily focused on atmospheric studies, might contribute valuable data regarding any interactions between Atlas's extensive coma, an enormous cloud of gas, and the Martian environment. What might be uncovered during this fleeting observational window could finally resolve the mounting questions that have persisted since August. The morphology of Atlas's unprecedented carbon dioxide coma, a massive envelope extending outward for an astonishing 348,000 kilometers, should become distinctly visible to instruments aboard Martian orbiters. Its dramatic anti-tail behavior, which points directly toward the Sun rather than away from it as expected according to conventional comet physics, might also reveal structural details that could explain its bizarre and seemingly defiant characteristics. Spectroscopic analysis conducted during this close encounter could either confirm or challenge the tentative chemical signatures inferred from Earth-based observations. Is the reported green coloration in the coma genuinely caused by dicarbon or cyanide compounds energized by solar radiation? Does the colossal CO2 envelope truly dominate the object's composition to an extent that defies previous understanding? These fundamental questions about Atlas's chemical makeup and internal structure may finally receive the clarity they have long lacked, providing insights that could reshape our understanding of interstellar objects. Even though the resolution capabilities of Mars orbiters are limited by the vast distance of roughly 30 million kilometers, they remain capable of delivering scientifically valuable data concerning Atlas's nucleus size and surface characteristics. Harvard's lobby has suggested that, even at this range, high-rise observations could resolve features on the order of tens of kilometers per pixel, sufficient detail to distinguish between a typical cometary nucleus and something more exotic or artificially constructed. Such data could ultimately help determine whether Atlas conforms to known natural models or if it hints at phenomena beyond current scientific paradigms. Yet, despite the promising prospects of capturing critical data during the upcoming Mars flyby, this optimism faces a familiar and persistent pattern of uncertainty that has shadowed the Atlas coverage since August. The pressing question remains: will we actually witness the results? Images, spectroscopic data, and detailed findings being released swiftly, comprehensively, and without the influence of editorial filters or deliberate delays. History indicates that space agency communication strategies surrounding Atlas suggest otherwise. Even with potentially groundbreaking discoveries on the horizon, any significant revelations are likely to undergo prolonged periods of analysis before they reach the public eye. These delays can stretch over weeks or even months as scientists meticulously interpret the anomalies, verify findings, and attempt to understand phenomena that defy conventional expectations. The inherent latency in data transmission and processing is a real and substantial obstacle to immediate transparency. Even if the spacecraft involved in the flyby managed to capture extraordinary imagery and measurements on the 3rd of October, the inevitable delays, due to communication bottlenecks, the time required for data calibration, and rigorous scientific scrutiny, will create a natural gap between the moment of observation and the official public announcement. This raises a fundamental question for anyone closely following the unfolding story. How long is a reasonable and justifiable delay for images and data of obvious public interest? What constitutes acceptable latency when the world is eager for direct visual confirmation of an interstellar visitor's true nature? The crucial issue at stake is whether the upcoming Mars observations will be treated with the same transparency and rapidity that previous interstellar visitors, such as Borisov or Oumuamua, enjoyed in their respective periods of heightened interest. Will we see an open, unfiltered release of the most recent images and findings, or will these revelations slip into the familiar black hole of extended analysis and selective disclosure that has characterized Atlas's coverage over the past couple of months? The answer to this question could be pivotal, potentially determining whether public trust in space agencies' commitment to transparency can withstand the encounter with a genuine cosmic mystery that challenges our understanding. The psychological dynamics at play during this flyby are complex and profound. After weeks of relative silence from major observatories and space agencies, the upcoming Mars flyby stands as a critical juncture, an all-or-nothing moment for sustaining or eroding public engagement with Atlas's story. If the results are shared openly and promptly, demonstrating a willingness to confront and communicate about the unknown, it could serve to restore confidence in the scientific process and the integrity of institutional communication. Conversely, if delays persist or if the information is released selectively, perhaps only after extensive vetting or with certain details withheld, it risks inflicting lasting damage to public trust, fostering skepticism, and deepening the sense that something is being concealed. Furthermore, the international dimension of the Mars observation effort introduces both opportunities and challenges. Multiple space agencies, each operating different spacecraft with varying capabilities, could collaborate to produce a richer, more comprehensive data set. Such cooperation could, in theory, enhance our overall understanding of Atlas, revealing details that no single agency could uncover alone. Yet coordinating public releases across diverse institutional cultures, communication protocols, and national interests naturally complicates the process. These logistical hurdles could introduce delays which, in the current climate of heightened suspicion and expectation, might appear suspicious or deliberately strategic to observers already primed to believe that information is being managed or withheld. The orbital mechanics involved during the flyby further influence the scope and quality of data collection. The relative positions of Mars, the observing spacecraft, and Atlas will determine which instruments can achieve optimal viewing geometries. Whether for high-resolution imaging, spectroscopy, or other measurements, not every orbiter will necessarily be in the right place at the right time to capture the most detailed views. Some may face unfavorable angles or limited operational windows, thereby constraining the amount and quality of data available for analysis. Compounding these challenges is the unfortunate coincidence that the Mars flyby will occur during Atlas's approach towards solar conjunction, as seen from Earth. During this period, the Sun's interference renders ground-based telescopes unable to provide immediate confirmation or supplementary observations. The unfavorable solar angles mean that even if the orbiting spacecraft on Mars manage to secure definitive images, the ability of Earth-based observatories to verify or complement those findings in real time will be significantly hampered. This creates a further delay in establishing a comprehensive picture, an unavoidable obstacle that could influence how quickly and transparently the scientific community and the public receive vital information about Atlas's true nature. The temporary isolation of data collected from Mars-based instruments could play a significant role in delaying the publication of findings as scientists await corroborating evidence from other sources. This cautious approach is often rooted in operational constraints that can impact the quality and clarity of observations made from Mars orbit. These constraints might include unpredictable factors such as dust storms, spacecraft maintenance needs, or competing priorities within the scientific community, each of which can compromise the planned observation campaigns. Such disruptions could lead to gaps between the anticipated results and what is ultimately achieved, influencing both the timing and the content of the public disclosures about the flyby. Fortunately, the European Space Agency's history of communication regarding Mars missions provides some grounds for cautious optimism. Historically, ESA has maintained a transparent stance, sharing imagery and scientific data with minimal delay, thereby fostering trust and clarity about their explorations. However, Atlas presents an unprecedented challenge. Its peculiar and potentially revolutionary characteristics demand a more measured approach to communication. This situation might justify a more cautious dissemination of findings to ensure accurate interpretation and prevent premature conclusions. NASA's strategy regarding the Mars flyby is likely to mirror their broader institutional response to Atlas's unusual nature. If ongoing analysis suggests significant interpretive uncertainties, NASA may continue to exercise restraint in releasing detailed information, even if the spacecraft's observations yield spectacular results. Conversely, if the data eventually clarifies Atlas's true nature and confirms unexpected or extraordinary properties, there could be a shift toward more open communication, allowing the scientific community and the public to understand the object's true characteristics more fully. The countdown to October 3rd carries implications that extend well beyond scientific curiosity. This flyby serves as a critical test of whether humanity can still expect transparent, straightforward sharing of cosmic discoveries in an era increasingly characterized by institutional caution. The way in which these observations are communicated will influence public trust and engagement, shaping perceptions of scientific integrity amid complex uncertainties. Across the globe, citizen scientists, amateur astronomers, and concerned observers will be intently watching, not only for what the Mars spacecraft might discover, but also for how swiftly and thoroughly those discoveries are shared. Their focus is on the transparency and completeness of information, recognizing that the support and curiosity of the public are vital to the ongoing pursuit of space exploration. The way this event unfolds could set a precedent for future discoveries, highlighting whether extraordinary cosmic phenomena can be openly shared or whether the era of cautious silence will continue to dominate the narrative. Moving forward, the period around perihelion, scheduled for late October, will be a pivotal moment for Atlas. On October 29th and 30th, our interstellar visitor will reach its point of maximum solar heating, approaching within approximately 1.3 to 1.4 astronomical units from the Sun, just inside Mars's orbital radius. This close encounter will serve as a natural stress test for Atlas, potentially revealing whether it is an exceptionally exotic but ultimately conventional comet or something that challenges fundamental assumptions about interstellar objects. Physics operates with relentless precision during perihelion passages. The intensity of solar radiation follows an inverse square law, meaning that as an object nears the Sun, it is subjected to a rapidly increasing influx of energy. For comets, this intense heating drives the sublimation of volatile compounds, especially ices, trapped within their nuclei. This process creates the spectacular outgassing events that produce the luminous comas and characteristic tails we associate with these cosmic wanderers. Atlas has already exhibited unprecedented behavior during its approach, indicating that its responses to solar heating may be unlike anything observed before. The upcoming perihelion will be critical in confirming whether its activity aligns with known cometary processes or if it exhibits anomalies that could redefine our understanding of interstellar visitors. As the Sun's energy reaches its peak intensity during perihelion, the effects on Atlas's extraordinary coma, already sprawling across an astonishing 348,000 kilometers, could be profound and transformative. Conventional comet models anticipate that increased solar heating should accelerate sublimation, causing the gaseous envelope to expand further and potentially altering its chemical makeup as various volatile compounds reach their sublimation points. Such a process might result in a dramatic swelling of the coma, accompanied by shifts in its spectral signatures, revealing the presence of different materials as they vaporize under the intense heat. However, Atlas has repeatedly defied these traditional expectations, rendering predictions about its behavior near perihelion largely speculative and uncertain. The comet's response to solar energy may not follow known patterns. Instead, it might produce unexpected phenomena that could offer critical insights into its true nature. One such possibility is the occurrence of outbursts, sudden explosive releases of trapped gases and dust caused by internal pressure buildup. Many comets are known to brighten abruptly during close solar approaches when internal stresses cause parts of their structure to rupture, releasing volatile materials in a burst of activity. Should Atlas experience such an outburst, the resulting debris dispersal patterns and the chemical signatures embedded in the ejected material could serve as vital clues, indicating whether its nucleus is composed of standard cometary substances or harbors more exotic, perhaps even artificial materials. Another intriguing aspect is the comet's unusual anti-tail behavior, an anti-tail that points directly toward the Sun, in stark contradiction to the expectations set by classical physics. During perihelion, as the object is subjected to increased solar radiation, this phenomenon might become even more pronounced or undergo noticeable changes. If the anti-tail results from the characteristics of dust grains, such as their size, charge, or electromagnetic interactions, then intensified solar energy could amplify these effects, making the anti-tail more prominent or altering its shape. Conversely, if the anti-tail's formation is primarily driven by conventional radiation pressure, then the increased solar heating could finally overpower whatever forces are maintaining its unusual orientation, prompting Atlas to develop a more typical tail structure that streams away from the sun. Fragmentation presents both an opportunity and a danger during Atlas's perihelion passage. The intense thermal and tidal stresses experienced during its close approach to the sun might cause the object to break apart, revealing previously hidden internal structures that have remained concealed within an intact nucleus. Such an event could provide invaluable data, offering a direct glimpse into the composition, layering, and physical integrity of Atlas's core. On the other hand, fragmentation could also scatter the debris, dispersing the clues needed to understand its true nature across multiple fragments, each with potentially different characteristics. This scattering complicates the scientific picture, turning what could be a straightforward study into a more complex puzzle of interpreting a field of debris. If Atlas survives perihelion without fragmenting, then post-conjunction observations beginning in early December could be crucial for gathering the definitive chemical and morphological data that have been elusive since August. By that time, the object will have completed its closest approach to the sun and started its outbound journey, likely exhibiting changes induced by solar heating that could shed light on its unusual properties. These observations would aim to confirm whether the dominance of carbon dioxide, suggested earlier by Spherex's preliminary data, remains accurate, and whether the reported green coloration in its coma can be definitively identified through spectral analysis. High-resolution imaging of the nucleus itself could provide critical details about its size, shape, and rotational dynamics, helping to distinguish whether Atlas is a natural object or perhaps something more artificial. The targeted scientific efforts during perihelion include a comprehensive suite of measurements, confirming the chemical composition, particularly the prominence of CO2, identifying the specific compounds responsible for the greenish hues, and analyzing dust particles to understand their sizes, charges, and material properties. Such detailed dust grain analysis could also help resolve the mystery of the anti-tail, whether it is formed by unusual dust characteristics or electromagnetic effects, providing a clearer picture of the physical processes at play. In essence, perihelion is a pivotal moment for Atlas. It holds the potential to either confirm its status as an extraordinary natural comet or to reveal phenomena that challenge our current understanding of interstellar objects. The outcomes of these high-stakes observations could significantly influence our theories of cometary physics, the nature of interstellar visitors, and possibly even the existence of artificial structures or unknown materials. Yet whether these insights will be promptly shared with the public or remain shrouded in scientific caution remains an open question, adding an element of uncertainty to this already enigmatic celestial visitor. If Atlas ejects dust particles that possess unusual electromagnetic properties, the interactions between this dust and the solar wind during perihelion could produce observable phenomena that shed light on the complex physics behind its perplexing tail behavior. The timing of this perihelion, the closest approach to the sun, coincides with a period of solar conjunction, a phase during which the sun's position relative to Earth makes direct observation extremely challenging. This natural alignment effectively creates a frustrating observational blackout, preventing scientists from studying the object during its most dynamic and scientifically significant phase. Consequently, any dramatic changes Atlas might undergo due to intense solar heating may remain hidden until the object re-emerges from the sun's glare. likely not until December when it becomes visible again in post-conjunction observations. Despite the critical importance of this phase in Atlas's evolution, international space agencies have yet to make public any specialized observation campaigns aimed at this perihelion window. The absence of coordinated efforts implies either that these agencies consider Atlas's behavior sufficiently understood and predictable to not warrant special monitoring, or that such plans are in place but remain classified or undisclosed to the public. Interestingly, the Parker Solar Probe, which is positioned in a unique orbit near the Sun during late October and early November, could, in theory, provide valuable insights into Atlas's behavior during or immediately following perihelion. Yet no official statements or plans have been announced regarding its potential to observe the object, a missed opportunity for close-up solar observations that could reveal details otherwise invisible from Earth-based telescopes. Meanwhile, amateur astronomy communities are preparing themselves for post-conjunction observations expected in December. However, the prolonged gap between perihelion and the reappearance of Atlas in the night sky means that critical processes, such as potential fragmentation, chemical transformations, or the development of its unusual tail, will unfold largely without direct public documentation or scientific scrutiny. The broader scientific community will have to rely heavily on whatever space-based assets might capture during this period, assuming such observations are scheduled, executed, and eventually released. The transparency and timeliness of this data sharing will be crucial, yet they remain uncertain. The passage through perihelion also carries significant psychological implications beyond the technical and scientific challenges. The manner in which agencies handle the dissemination or withholding of information during this critical window could influence public trust profoundly. If Atlas experiences dramatic changes due to solar heating, but these are not immediately shared with the world, the pattern of selective information release seen so far could become a lasting stain on the credibility of space agency communications. Such opacity risks eroding public confidence, especially when the phenomena in question are extraordinary and defy conventional understanding. In the coming months, the quality of post-perihelion studies relying on Earth-based telescopes will depend heavily on the observational conditions prevailing in December, especially in the Northern Hemisphere's winter. Factors such as weather, atmospheric interference, and the object's position relative to bright star fields could limit the resolution and sensitivity of follow-up observations precisely at a moment when Atlas might display its most evolved and revealing characteristics. This confluence of challenges underscores the fundamental uncertainty surrounding whether Atlas's behavior will ultimately conform to natural phenomena, or whether it might present characteristics that challenge our basic assumptions about interstellar objects, raising questions about their origins, compositions, and the physics governing their activity during close solar approaches. The question of how we interpret and communicate about interstellar visitors holds profound implications for humanity's broader understanding of our place within the vast cosmos, an immense universe that continues to surprise us with phenomena we are only beginning to comprehend. The way future discoveries are studied, shared, and understood could shape not only scientific progress but also our collective worldview, influencing cultural, philosophical, and even spiritual perspectives. Now venturing into the shadowy realm of theoretical information warfare, we encounter a labyrinth where the line between genuine scientific prudence and deliberate deception becomes increasingly blurred. Among the more controversial and speculative notions is the concept known as Project Blue Beam, a conspiracy theory that emerged in the 1990s. This hypothesis posits that governments might be capable of fabricating false cosmic events through sophisticated technology, such as holographic projections, satellite-based displays, and coordinated media manipulation, to sway public perception and exert control over societal narratives. While there is no credible evidence to substantiate these claims, the theory provides a provocative lens through which to examine how authentic cosmic discoveries could potentially be managed or even manipulated, especially when such revelations threaten existing power structures or social stability. According to this theory, these fabricated or exaggerated astronomical phenomena could serve as tools designed to reinforce certain belief systems or to facilitate social control by creating convincing illusions that seem entirely real to the human eye and mind. Holographic projections in particular could be broadcast across skies or through telescopes, mimicking celestial events that are, in truth, artificially generated. Satellite displays and media orchestrations might work in tandem to craft a synchronized narrative that guides public perception, steering collective consciousness towards specific ideological or political objectives. Applying this speculative framework to the case of Atlas, the mysterious interstellar object, raises unsettling questions. Could Atlas's unusual features and behaviors, its unprecedented coma scale, strange anti-tail pointing toward the sun, or rapid brightness changes, be part of a broader psychological operation rather than genuine natural phenomena? Might the media coverage, delayed disclosures, or the carefully curated flow of information about Atlas be part of a larger pattern, an attempt to gradually condition the public to accept increasingly anomalous or even artificial explanations? It's noteworthy that Atlas's appearance coincided with a period of significant global uncertainty, marked by political upheavals, economic instability, and environmental crises, moments when a dramatic cosmic mystery might serve as an effective distraction, diverting attention from terrestrial struggles towards existential questions about humanity's role in the universe. Whether this timing was purely coincidental or intentionally orchestrated, the object has undeniably provided a compelling focus that shifts the narrative away from human crises, prompting reflection on our place in the cosmos. The gradual dose-like release of increasingly extraordinary claims about Atlas, its bizarre composition, the enormous CO2 coma, the anti-tail behavior, and the rapid brightening, mirrors a psychological conditioning pattern. This approach seems designed to ease the public's acceptance of phenomena that, at first glance, seem impossible, by slowly expanding the boundaries of what's deemed acceptable or credible. Instead of straightforwardly unveiling Atlas's most peculiar features, information has been doled out in measured increments, allowing the collective imagination to adapt and expand to accommodate the seemingly impossible. However, the concept of Project Bluebeam requires capabilities that far surpass our current technological reality. The creation of convincing holographic displays visible through professional telescopes around the world would necessitate levels of coordination, technological sophistication, and secretive control that no verified government entity has demonstrated. Such a scheme would imply a central authority exerting control over a decentralized network of observation points, an undertaking that would be virtually impossible given the independence of international space agencies, observatories, and scientific communities operating across multiple nations and cultures. Indeed, the international verification of Atlas's existence and its characteristics presents a significant counter-argument against the feasibility of such a conspiracy. Observations from diverse space programs, including those of Europe, the United States, China, and other nations, have independently confirmed the object's unusual features using separate instruments and analysis protocols. The corroboration across multiple independent sources makes it exceedingly unlikely that Atlas's traits are artificial fabrications orchestrated by a clandestine agenda, suggesting instead that what we are witnessing is a real, albeit extraordinary, natural phenomenon. Coordinating a deception across a broad spectrum of diverse institutions and political entities would demand an unprecedented level of cooperation, one that surpasses any previous international coordination seen in history across any domain. Such an undertaking would be extraordinarily complex, requiring seamless collaboration among nations and agencies that typically operate with their own protocols and priorities. In this intricate landscape, amateur astronomy adds an additional layer of verification that further complicates any hypothetical scenario of deception. Thousands of independent observers equipped with personal telescopes and cameras have independently captured images of Atlas and verified its unusual behavior through their own analyses. This widespread distributed network of skywatchers functions outside of government control, making it exceedingly difficult for any orchestrated misinformation to go unnoticed or unchallenged. Any attempt at manipulation would be readily apparent due to the sheer volume and diversity of independent observations. However, it's important to recognize that even with genuine, verifiable observations, authorities could still exercise subtle influence over public perception. By selectively emphasizing certain aspects of the data and downplaying others, they could guide the narrative in a way that supports desired conclusions without the need to produce outright false phenomena. This kind of narrative shaping, what some might call subtle manipulation, operates in the shadows, making the line between genuine scientific caution and deliberate storytelling almost invisible to outside observers. The process of UAP, unidentified aerial phenomena. Disclosure offers a real-world precedent for this delicate balancing act. For decades, military encounters with unexplained aerial objects remained classified, and information about them was kept under wraps. Only recently have some of these phenomena been acknowledged publicly, with partial disclosures that confirm the reality of certain anomalies but carefully regulate how the information is presented. This approach ensures that the public's understanding is managed gradually rather than overwhelmed by sudden full transparency. Such a precedent suggests that if genuine cosmic anomalies like Atlas are recognized as potentially extraordinary, they might be treated similarly. Instead of outright revealing everything at once, authorities could acknowledge certain facts while withholding details that might provoke confusion or fear. This method of incremental disclosure aligns with how modern information warfare operates, through narrative control, guiding public interpretation rather than fabricating entirely false events. Rather than creating false astronomical phenomena, sophisticated manipulation might instead focus on shaping how real discoveries are perceived and understood. Whether Atlas is framed as a conventional, if unusual, comet, or as a potentially artificial visitor could depend entirely on the selective release and emphasis of specific pieces of information. Such framing allows authorities to influence the broader narrative, maintaining control over the story without introducing blatant falsehoods. The psychological impact of cosmic discoveries on human beliefs, particularly religious and philosophical worldviews, further complicates the issue. Revelations about advanced civilizations traversing the galaxy could cause social upheaval or existential crises, especially if populations are unprepared for such truths. This makes timing, method, and manner of disclosure critically important, as they can either ease the transition or provoke unrest. These concerns do not necessarily stem from conspiracy, but from legitimate considerations about societal stability. Economic stability is another crucial factor. Confirmation that interstellar visitors possess technologies beyond our current understanding could cause significant upheaval, destabilizing markets, currencies, and entire industries. As a result, a cautious, phased approach to disclosure might be employed to gradually prepare economic systems for paradigm-shifting revelations. This strategic delay in releasing full details could serve to prevent sudden disruptions and allow markets and infrastructures to adapt incrementally, reducing the risk of chaos. In sum, the handling of extraordinary cosmic phenomena like Atlas could involve a complex interplay of verification, narrative control, societal preparedness, and economic stabilization, all aimed at managing potential upheavals without necessarily resorting to outright deception. Instead, the focus might be on shaping perceptions and expectations, ensuring that when the full truth, or at least a version of it, is finally revealed, it does so in a way that minimizes panic and maximizes societal stability. Strategic considerations rooted in national security further complicate the calculus of disclosure, extending far beyond mere motives for concealment. If Atlas exhibits capabilities that could potentially be weaponized or reveal vulnerabilities within our space defense systems, then the prioritization of strategic stability and security could overshadow the public's desire for immediate transparency about its mysterious characteristics. In this context, the decision to reveal or withhold information becomes a delicate balancing act, weighed against broader geopolitical and military implications rather than solely scientific curiosity. The advent of the Internet age has fundamentally transformed the landscape of information control, markedly reducing the efficacy of traditional top-down censorship. Unlike previous eras when centralized authorities could more easily regulate access to sensitive discoveries, today's interconnected digital environment, characterized by social media, global communication networks, and widespread distributed observation, creates a multitude of channels through which information can spread. This networked ecosystem makes the complete suppression of extraordinary findings increasingly challenging, as independent observers and citizen scientists can share data, insights, and images almost instantaneously, bypassing official filters and controls. Nevertheless, sophisticated influence operations have evolved alongside these technological changes. They now possess the means to subtly shape public interpretation of authentic phenomena without resorting to outright fabrications or false flag operations. By emphasizing certain explanations, timing the release of information during periods of peak interest, and selectively unveiling observational data, these operations can steer public understanding toward desired narratives, whether that means fostering skepticism, downplaying anomalies, or promoting specific scientific interpretations. This form of subtle manipulation leverages the power of narrative framing rather than deception through outright falsehoods. The core challenge in assessing scenarios like Project Bluebeam, a conspiracy theory proposing the use of holographic technology to simulate celestial phenomena, is distinguishing between legitimate scientific caution and deliberate manipulative information management. Both approaches can produce indistinguishable observable patterns, delayed disclosures, selective emphasis on certain data, and coordinated messaging from institutional authorities. Without transparent insight into internal decision-making processes, outside observers are left to speculate, rendering verification of motives virtually impossible. This opacity fuels suspicion and complicates efforts to discern genuine scientific restraint from strategic deception. In this complex informational environment, media literacy becomes an essential skill for citizens striving to navigate the vast and often convoluted landscape of cosmic discovery. Understanding how institutional incentives, driven by economic interests, political pressures, and security concerns, influence the timing and framing of scientific communications is crucial in distinguishing honest caution from manipulative narrative control. Recognizing these influences helps prevent misinterpretations that could lead to unwarranted fears or conspiracy theories, fostering a more nuanced and informed perspective on extraordinary phenomena. The potential danger of Project Bluebeam thinking does not lie solely in its specific claims about holographic or advanced technological deception, but in its underlying acknowledgement that information can be weaponized to serve interests well beyond the pursuit of scientific truth. Whether Atlas is a genuinely anomalous object or a carefully curated example of conventional discovery, the manner in which its information is presented to the public reflects institutional priorities. priorities that may not align with the public's right to complete transparency. As humanity approaches critical milestones such as the Mars flyby and subsequent perihelion passage of Atlas, the pressing question is whether observations will be handled with a commitment to scientific transparency, or whether other considerations, security, strategic advantage, or narrative control, will take precedence. The way this unfolding story is managed could influence not only our understanding of this particular interstellar visitor, but also set a precedent for how future cosmic discoveries are communicated, contested, and integrated into our collective knowledge within an intricate web of science, geopolitics, and public trust. The outcome of this balance may ultimately shape the future of humanity's relationship with the cosmos, either as open explorers or as cautious custodians, wary of revealing truths that might challenge our perceptions of safety, sovereignty, and understanding. Part 15. The complex journey of space images from cosmic photons to the public eye. Every breathtaking image of the cosmos that appears on NASA's official platforms or floods social media feeds is the result of a meticulous and layered process. A detailed voyage that transforms raw celestial signals into polished, scientifically accurate visuals suitable for public consumption. Recognizing this intricate pipeline helps us understand why the current silence surrounding Atlas may well stem from straightforward technical realities rather than any nefarious concealment. Although from the outside the lack of new images might seem suspicious or deliberately hidden, the reality often remains invisible to observers eager for instant cosmic gratification. The process of producing these iconic images begins well before any telescope's lens or mirror is aimed at a specific target. Space agencies operate on tightly scheduled observation plans, where precious observing time on flagship instruments like the Hubble Space Telescope or the James Webb Space Telescope is allocated months, sometimes even years in advance. These allocations are decided through rigorous competitive peer review processes, where scientists submit comprehensive proposals articulating the scientific importance and unique value of their chosen targets. These proposals then compete against hundreds of other research projects vying for the limited observation windows. Each one carefully evaluated for scientific merit, feasibility, and potential impact. In extraordinary cases, such as unexpected cosmic events or objects that appear suddenly, target of opportunity requests can be made. These are emergency or rapid response observations triggered by phenomena like supernova, asteroid impacts, or unusual comet behaviors that couldn't be foreseen during regular proposal cycles. These requests have to pass stringent scientific justifications, often requiring compelling evidence that the observation will significantly advance our understanding rather than simply satisfy curiosity. The threshold for interrupting scheduled observations is intentionally high, ensuring that only truly critical or unprecedented events warrant such immediate attention. Even after securing observation time, the raw data collected by these telescopes doesn't immediately translate into the images we see. Instead, it undergoes a lengthy and painstaking process of processing before any visual representation is produced or shared. Each step is essential to ensure that the final product is both scientifically accurate and visually comprehensible. This begins with calibration, where bias frames are subtracted to remove electronic noise inherent in the detectors. Dark current exposures are taken to eliminate thermal artifacts that can distort the readings, and flat field corrections are applied to account for sensitivity variations across the camera's pixel array. While these calibration procedures operate automatically within data processing pipelines, they demand significant computational resources and time to execute properly. Next, the images are aligned through a process called co-registration, which compensates for slight telescope tracking variations, atmospheric disturbances, for ground-based observations, and other sources of image distortion. Cosmic rays, high-energy particles from space, can strike detectors, creating false bright spots or streaks. Algorithms are employed to identify and remove these artifacts, ensuring they don't contaminate the final image. Multiple exposures are then combined using sophisticated statistical techniques designed to maximize the signal-to-noise ratio, revealing faint details while suppressing noise or errors introduced by the environment or instrumentation. Before any image is deemed suitable for release, scientists must carefully consider its context. This involves assessing whether the observed features are permanent or transient, meaning are they stable surface structures or fleeting phenomena. To make this determination, they analyze data sets over time, establishing baselines that distinguish real features from observational anomalies. Spectroscopic analysis further enriches this understanding, providing detailed insights into the chemical composition and physical conditions of the observed objects or regions. Additionally, geometric calculations involving the viewing angles and the position of the sun help interpret the visibility and appearance of specific features, considering how illumination and perspective might influence what we see. Only after passing through this rigorous process, the calibration, alignment, artifact removal, contextual analysis, and chemical interpretation, does an image become ready for public dissemination. It's a multi-layered, resource-intensive journey that ensures the visuals we admire are not only striking but also scientifically trustworthy and meaningful. The delay or absence of new images of Atlas, therefore, may simply reflect the time-consuming, methodical nature of this pipeline, rather than any effort to hide or manipulate the truth. The timeline for scientific analysis extends considerably longer when observations unveil unexpected and unusual characteristics. Standard processing workflows are typically designed around conventional astronomical targets, objects with predictable behaviors and well-understood signatures, allowing for relatively swift interpretation and public dissemination. However, when dealing with anomalies like Atlas, researchers must adopt specialized, often bespoke analytical approaches. Developing these new methods to interpret unprecedented phenomena can add weeks, sometimes even months, to the overall publication timeline. Scientists and mission teams often exercise extreme caution, opting to delay the release of representative images until they are confident that their interpretations are sufficiently robust. This deliberate restraint is intended to prevent misunderstandings or misrepresentations of preliminary data by the public or media, which might otherwise draw inaccurate conclusions about the nature of the object. Basic photometric measurements, assessing brightness levels and how they change over time, are among the initial steps that help establish the object's activity levels and temporal evolution. Complementary spectroscopic analyses aim to identify the dominant chemical constituents within the object's coma or tail, providing crucial clues about its composition. Instrument health checks are also an essential part of the process. They verify that any unusual features observed are genuinely astronomical in origin and not artifacts caused by equipment malfunctions or calibration errors. These checks are particularly vital when observations feature unexpected or extreme phenomena that challenge existing understanding. Adding to these complexities are geometric constraints that can influence observational capabilities during certain periods. For example, solar conjunction, the alignment where the object passes near the sun from Earth's perspective, imposes strict pointing restrictions on telescopes. These measures are primarily designed to protect sensitive instruments from potential damage caused by intense solar radiation. Even space-based telescopes, which operate above Earth's atmosphere, adhere to strict angular separation limits from the sun to prevent overheating of detectors and optical components. Meanwhile, Earth-based observations encounter additional hurdles. Atmospheric absorption, weather variability, and seasonal visibility windows can all restrict the ability to observe objects approaching solar conjunction. As a result, coverage tends to diminish during these periods, creating natural gaps in data that have nothing to do with institutional secrecy or deliberate information suppression. Moreover, data rights and embargo policies impose legitimate delays on image release and publication. Many missions maintain proprietary periods during which the discovery teams have exclusive access to their data. These policies are designed to safeguard the scientists' investments of time and resources, allowing them to analyze and publish their findings before wider dissemination, thus maintaining scientific integrity and avoiding premature media speculation. Internal caution continues to influence timing decisions, especially when observations reveal morphological features that are difficult to interpret straightforwardly. For example, the sunward plume behavior observed in Atlas imagery, an unusual outgassing pattern pointing toward the sun, necessitates careful, nuanced explanations. Such features can be easily misunderstood as violations of physical laws if not properly contextualized, so communication teams slow their messaging to craft accurate, scientifically responsible narratives that convey inherent uncertainties. Coordination across multiple observatories and space agencies further complicates public release schedules. When diverse assets such as the Hubble Space Telescope, Webb, Gemini, and ESA's satellites observe the same object independently, their findings require harmonization. Public disclosures must be synchronized to ensure consistent messaging, appropriate attribution, and to avoid confusion stemming from overlapping or conflicting reports. Finally, the definition of new imagery itself can generate confusion. Processed observations often appear weeks or even months after the initial data collection, owing to the extensive calibration, analysis, and verification procedures involved. This delay in producing and releasing refined images adds another layer of complexity, one driven by scientific rigor rather than secrecy, highlighting the meticulous nature of modern astronomical research in handling extraordinary and puzzling phenomena. Public relations offices may choose to release images that are based on observations obtained under the most favorable viewing conditions, times when the target object is ideally positioned relative to Earth and the Sun. However, these images are often processed and prepared during periods when the object itself has become unobservable due to positional constraints or observational limitations. To the outside world, this practice can create a misleading perception of gaps in observational activity, suggesting that scientists are waiting idly or deliberately withholding information when in fact, teams are working diligently behind the scenes. This misunderstanding is further compounded by the public's collective memory of previous interstellar visitors, such as Oumuamua and Borisov, which benefited from simpler morphologies and more advantageous observing geometries. These factors enabled rapid analysis, quick turnaround times, and frequent publication of imagery, fostering the expectation that new images would appear swiftly once such objects are detected. In contrast, Atlas's behavior, marked by complex structures and more challenging observation windows, necessitates a different approach to communication. Its intricate phenomena and the difficulties inherent in observing it mean that responses and updates naturally feel more cautious or delayed, even if work is ongoing. Throughout the history of professional astronomy, valuable lessons have been learned about managing public expectations, especially when investigating phenomena that deviate from the norm. Striking a balance between promptly sharing exciting discoveries and refraining from premature conclusions is a nuanced task that requires deliberate and careful communication strategies. These strategies must prioritize scientific accuracy and integrity over sensationalism or speed, recognizing that rushing to publish incomplete or preliminary data can lead to misunderstandings or false narratives. Ground-based observations are particularly vulnerable to unpredictable disruptions caused by weather and operational constraints. Dust storms, equipment maintenance, and competing priorities in telescope scheduling can interrupt planned observation campaigns unexpectedly. Similarly, atmospheric conditions like cloud cover, turbulence, and seasonal variations in visibility can influence the quality and quantity of data collected. These factors introduce natural gaps in observational coverage that are often mistaken for deliberate withholding or technical failures when, in reality, they are routine challenges faced by astronomers worldwide. Adding another layer of complexity is the international nature of space science collaborations. Multiple agencies and research institutions, each with their own administrative protocols and communication frameworks, must coordinate efforts to observe and analyze these objects. Differences in operational procedures and reporting standards inevitably introduce delays into the process of sharing findings. For example, European, American, and other national space programs operate under distinct guidelines, which can slow down the synchronization of data releases and public announcements compared to a single unified source. Furthermore, the modern technological infrastructure supporting astronomy, comprising data storage systems, network connectivity, and computational resources, also plays a significant role in determining the timing of public disclosures. Bottlenecks in any part of this complex pipeline can cause delays that are invisible to outside observers, leading to the impression that information is being deliberately suppressed. These dependencies mean that even when the data and analysis are ready, logistical and technical factors may extend the time before they reach the public eye. Understanding these realities is crucial for placing the silence surrounding Atlas within a broader context. It moves the narrative away from conspiracy theories or intentional concealment, highlighting instead the inherent complexities of contemporary scientific observation and communication. These processes are inherently meticulous and methodical, designed to produce reliable and accurate results, albeit at the cost of time. The challenge for both scientists and the public is to distinguish between genuine technical delays, which are a natural part of complex scientific workflows, and any indications of problematic information management, especially when extraordinary discoveries question or challenge established scientific understanding. Transparency about the limitations and constraints of the process can serve to foster trust, helping the public appreciate that delays are often a sign of rigorous scientific integrity rather than concealment. Open communication about these process-based realities can help manage expectations, ensuring that the pursuit of truth remains prioritized over the allure of immediate gratification, ultimately strengthening the relationship between scientific institutions and the society they serve. Part 16. What to focus on when the upcoming images of Atlas finally surface. Whether these new visuals arrive from the Mars orbiters during the anticipated flyby on October the 3rd, or from post-conjunction Earth-based observations in December, adopting a careful, systematic method of evaluation will be essential. Such an approach will assist in differentiating authentic scientific discoveries from the noise of media sensationalism, processing artifacts, and optimistic wishful thinking. Over the years, the astronomical community has refined analytical techniques designed to distinguish genuine signals from background noise. Methods that any dedicated citizen scientist can learn and apply when investigating cosmic enigmas. One of the most visually striking features to scrutinize in any new Atlas imagery is the so-called sun plume phenomenon. This feature stands out as the clearest visual indicator of the object's behavior, and by examining it closely, observers can gain valuable insights. Pay particular attention to whether the anti-tail, the tail that points directly toward the sun, remains present in subsequent images. Note whether it appears as a slender jet-like stream, sharply directed, or whether it broadens into a fan-shaped distribution of material, spreading out more diffusely. Monitoring changes in the plume's characteristics across different observation epochs can reveal much about the physical processes at play. Variations in the shape, size, or brightness of the plume might indicate evolving dust grain properties, shifts in the object's rotation, or alterations in viewing geometry caused by the changing position of the observer or the object itself. If in future images the sun plume diminishes in intensity, disappears altogether, or even reverses direction, such transformations would suggest that the familiar force of solar radiation pressure is finally overcoming whatever initial forces, perhaps magnetic or outgassing effects, had created the anomalous tail. This kind of evolution, if observed, would favor natural explanations for Atlas's unusual morphology. It would imply that the tail is a product of known physical interactions, rather than evidence of artificial or extraterrestrial engineering. At the same time, tracking these changes can yield critical insights into the internal dynamics of the comet's coma environment, informing models of how such objects respond to solar heating. Another diagnostic tool of particular importance is the analysis of fragmentation signatures. Look for signs of multiple condensations or clumps forming near the nucleus, features that are not part of the typical diffuse structures seen within a comet's coma, but rather resemble a string of pearls or discrete objects. The presence of such condensations could indicate that the object is undergoing internal stresses, either thermal, tidal, or both, leading to a breakdown of its structural integrity. Fragmentation is a common phenomenon among comets as they approach perihelion. It does not inherently suggest artificial design or exotic composition. However, patterns in the fragmentation process can tell an even deeper story. Symmetrical, organized arrangements of fragments, or geometric regularity in their distribution, might suggest that Atlas possesses a more complex internal structure than a simple natural nucleus. Such organized fragmentation could point to an internal framework or layered composition that responds predictably to stresses, raising intriguing questions about its true nature. Differentiating between chaotic random breakup events and more organized pattern-led disassembly requires meticulous analysis but could be crucial in understanding whether Atlas is a naturally evolved object or something more engineered. Brightness behavior is yet another vital piece of evidence. Comparing observed apparent magnitudes over time with theoretical predictions based on established cometary models can reveal underlying physical processes. A steady increase in brightness that aligns with the inverse square law, meaning the brightness grows proportionally to the square of the decreasing distance to the sun, would be consistent with a conventional response to solar heating, such as sublimation of surface ices. In contrast, abrupt spikes or sudden outbursts, followed by a gradual decline in brightness, typically indicate explosive events. Perhaps internal pressure buildup leading to volatile outgassing or structural failure. When claims surface, tentatively, that the brightness has increased by 20 times or more relative to standard models, these should be regarded as preliminary estimates. Such extraordinary claims require confirmation via carefully calibrated systematic photometry performed with reliable instruments. Only through rigorous, repeatable measurements can we accurately interpret whether these fluctuations reflect genuine astrophysical phenomena or are artifacts of observational variability. In summary, the next set of images and data, whether from Mars or Earth, should be examined with a discerning eye. Focus on the stability and evolution of the sun plume. Scrutinize signs of fragmentation or structural change, and analyze brightness trends against established models. Each of these observational markers offers a piece of the puzzle, helping us determine whether Atlas's behavior aligns with natural cometary processes or hints at something more extraordinary. Amateur astronomers contribute invaluable coverage over time, capturing observations that help track changes in the object's behavior and appearance. However, their measurements often lack the precision needed for definitive analysis of brightness variations, making professional verification and standardization essential to ensure accuracy. When it comes to interpreting the colors in atlas images, both opportunities and pitfalls arise. For instance, the appearance of green hues in processed photographs could suggest the presence of molecules like dicarbon or cyanogen, which are excited by solar radiation and emit light at characteristic wavelengths. Yet such color assignments in astronomical imagery are frequently influenced by artistic choices, image processing techniques, or false color schemes rather than direct spectroscopic evidence. Without accompanying spectral data, detailed measurements of specific wavelengths, these colors remain only suggestive, not conclusively diagnostic of the chemical makeup of the object's coma or tail. The way images are captured and processed dramatically influences the apparent colors. Different wavelength bands highlight various physical processes and chemical constituents. For example, certain filters emphasize emissions from specific molecules or dust particles. Without a thorough understanding of the methods used, such as filter selection, exposure settings, and post-processing techniques, interpreting colors directly from images can be misleading. Spectroscopic observations, when available, provide the most reliable method for determining the chemical composition of Atlas's atmosphere and outgassing behavior. Official reports that mention the presence of molecules like carbon dioxide, cyanogen, water vapor, or dicarbon should be carefully examined, especially noting how their relative abundances compare to what is typical in known comets. For instance, a dominance of carbon dioxide over water vapor would strongly support earlier suggestions that Atlas has an unusual, perhaps unprecedented compositional profile. In addition to chemical analysis, the structure and orientation of the tail provide vital clues. When examining tail architecture, focus on the alignment and shape of both dust and ion tails. A primary dust tail should generally be directed away from the sun, shaped by the pressure of solar radiation, creating an anti-sunward extension. Conversely, narrower ion or iron tails tend to follow magnetic field lines in the solar wind's flow, often appearing as distinct, more collimated features. During outburst events or when viewing geometry shifts, multiple tail structures at different angles can appear, revealing features that might have been hidden in previous observations. Even when individual resolution remains insufficient to discern surface details on Atlas's nucleus, estimates of its size can still be inferred through modeling of its coma and brightness variations. Professional astronomers employ techniques such as coma modeling and light curve analysis to estimate the nucleus's dimensions. These methods analyze how the brightness changes over time and how the surrounding gas and dust envelope behaves, providing constraints on the object's size and activity level. However, caution is warranted when encountering media claims that assert precise measurements based solely on fuzzy or low-resolution images. Such claims often lack the necessary uncertainty estimates and can be misleading. Detecting non-gravitational acceleration, forces acting on the object beyond simple orbital mechanics, requires highly precise long-term astrometric measurements. Such forces like jets or gas ejections would cause small deviations from expected gravitational trajectories. While a single image cannot prove these effects, consistent positional measurements that deviate from purely gravitational predictions would suggest the presence of jets, propulsive forces, or other active processes. Observations from Mars orbiters provide valuable geometric advantages, offering different viewing angles and reducing atmospheric interference compared to ground-based observations. Nonetheless, the vast distance, approximately 30 million kilometers, imposes fundamental limits on resolution. As a result, we should expect only modest improvements in image quality, rather than dramatic close-up details that surpass the physical constraints of observation at such range. These limitations mean that any high-resolution insights into Atlas's surface or nucleus structure will likely remain beyond reach until closer approaches or dedicated missions. Cross-validation across multiple independent observation systems stands as the most compelling form of evidence when discerning true cosmic phenomena from mere instrument artifacts or processing errors. When features or anomalies consistently emerge from data collected by a variety of platforms, be it Mars orbiters, ground-based telescopes, or space-based instruments, the credibility of those observations gains substantial weight. This multiplicity of confirmation helps establish the authenticity of unusual features, as claims originating from a single source can often be questioned or dismissed due to potential technical issues or biases. In the realm of extraordinary claims, verifying image authenticity becomes critically important. Visual artifacts such as over-sharpened edges, improbably detailed surface features, or inconsistencies within starfield backgrounds can often indicate excessive digital processing or even deliberate falsification, either to exaggerate findings or to create visual illusions. To prevent being misled, it's essential to rely on verified, trustworthy sources. Established mission archives, peer-reviewed scientific publications, and official channels are the bedrock of credible information, far more reliable than sensational social media posts or websites lacking scientific credentials. Navigating the complex landscape of astronomical discovery requires a disciplined approach, favoring verified institutional sources such as official mission blogs, reputable astronomy society circulars, and networks that foster collaboration between amateur and professional astronomers. These channels uphold standards of verification that help the public and scientific community distinguish genuine data from speculative or manipulated imagery. It is also important to temper expectations regarding the visual impact of authentic scientific imagery. Often, genuine astronomical discoveries appear less dramatic than the sensationalized images circulated by popular media. The raw data, when filtered through scientific analysis, tend to look messy, ambiguous, or inconclusive, reflecting the complex reality of cosmic phenomena. Instead of standalone images that seem awe-inspiring, true understanding emerges from the synthesis of multiple observations, data sets, and analytical methods. The importance of contextualizing individual observations within broader scientific frameworks cannot be overstated. Should future images of Atlas or any other interstellar object reveal genuinely shocking or extraordinary features, it is vital to maintain a systematic, cautious approach. Natural explanations, such as unusual plasma physics, complex geometrical effects, or fragmentation processes, can produce striking visual phenomena that challenge our intuition without necessitating artificial intervention or extraterrestrial artifacts. A systematic analysis serves a dual purpose. It maximizes scientific understanding and encourages skepticism, ensuring that interpretations remain grounded in physical plausibility. Whether Atlas proves to be a conventional comet or a revolutionary discovery, rigorous evaluation methods are essential. They help discriminate authentic cosmic phenomena from the inevitable mixture of wishful thinking, processing artifacts, and misinformation that often accompany mysterious objects. Such disciplined scrutiny empowers citizen scientists and enthusiasts alike, providing tools to participate meaningfully in the scientific process while fostering critical thinking skills necessary to navigate an environment saturated with speculation, hype, and deliberate deception. In the final part of this assessment, we must confront what we might be missing. Carefully cataloging our known facts reveals a timeline that should raise concerns about transparency and scientific integrity. For example, the last publicly released image from the Hubble Space Telescope of Atlas was taken on July 21st and shared with the world on August 7th. Since then, data from other observatories such as the James Webb Space Telescope and ground-based facilities have been collected but remain under analysis or have not been publicly disclosed. This pattern of delayed or withheld information should disturb anyone who values openness in scientific discovery. By critically examining this timeline and the gaps within it, we can better understand the implications of the current observational silence surrounding Atlas. Such scrutiny is vital in fostering a transparent, accountable scientific process, one that encourages rigorous verification and honest reporting, especially when faced with phenomena that could challenge our existing understanding of the universe. The James Webb Space Telescope observed the object on August 6th, gathering spectroscopic data that, even months later, remains under detailed analysis. Meanwhile, Gemini South managed to capture imagery on August 27th, yet this data was not made available to the public until early September. Since that time, a profound silence has fallen over the most advanced space telescopes, those that should be diligently documenting this historic interstellar visitor, leaving observers and scientists alike in a bewildering void of information. Adding to the mounting intrigue, the European Space Agency has confirmed plans for Mars orbiter observations scheduled during the flyby on October 3rd. This event presents our most promising opportunity to shatter the ongoing observational drought that has persisted since late summer, potentially providing critical insights into Atlas's nature. But an important question hangs in the balance. Will these upcoming observations be shared openly and transparently, as the public has every right to expect? Or will they too vanish into the same mysterious black hole of data analysis that has seemingly swallowed the Webb spectroscopy results, leaving us in the dark once again? As the calendar approaches late October, Atlas is set to endure its closest approach to the Sun, arriving at perihelion between October 29th and 30th, when it will experience maximum solar heating at roughly 1.4 astronomical units from our star. Should the object withstand this intense thermal stress, it is anticipated to reappear for Earth-based observations in early December. This window could finally provide the long-awaited opportunity to answer critical questions that have been building since July's initial sightings, revealing whether Atlas has evolved or altered in ways that might shed light on its mysterious origins. Among the most extraordinary confirmed features of Atlas is its colossal carbon dioxide coma, which extends outward from the nucleus for approximately 348,000 kilometers, an atmospheric envelope larger than most planetary orbits. No comet in recorded history has ever been observed to produce such an immense and pervasive CO2 atmosphere, rendering Atlas an unprecedented phenomenon that defies comparison with known celestial objects. Its very existence challenges our understanding of cometary behavior and composition, positioning it as a truly unique and enigmatic visitor from beyond our solar system. Adding to this enigma is the peculiar morphology of its sunward plume, which continues to defy the laws of conventional physics. Normally, solar wind pressure, charged particles streaming outward from the sun, drives material away from the star, creating tails that point away from the sun's direction. Yet Atlas exhibits an anti-tail, a prominent jet of material that appears to point directly toward our star, as if it is resisting or defying the fundamental forces that govern all other comets. This perplexing behavior raises profound questions about the physical processes at work within Atlas, and whether its characteristics are truly natural or suggest something more extraordinary. Now, to explore the possibilities, clearly labeled as speculative and hypothetical, regarding what those missing images and delayed analyses might reveal if they were shared without institutional filtering, we must consider the potential significance of such data. These scenarios, while conjectural, could provide explanations for phenomena that would justify the cautious and deliberate information management we have observed. For example, recent imagery, if it were made available, might show dust and gas patterns arranged in formations that appear artificially structured rather than chaotic, as expected from natural cometary outgassing. Instead of random dispersions, we might see geometric arrangements of debris, symmetrical jet patterns, or organized flows of material, features that strongly suggest technological intervention rather than purely natural processes. Such a discovery would fundamentally challenge our assumptions about interstellar objects, raising uncomfortable and profound questions regarding their origins and purposes. Could we be witnessing signs of artificial engineering or deliberate modifications, an indication that Atlas might not be a natural visitor at all? Another possible scenario involves fragmentation. If Atlas has begun breaking apart during its approach to the Sun, the resulting debris field could display geometric or organized patterns that resist conventional interpretation. Such non-random fragmentation might appear as symmetrical clusters, linear arrangements, or other structured features that suggest internal processes or external influences beyond natural disintegration. These hypothetical insights, if confirmed, would have profound implications, forcing a re-evaluation of what we understand about such objects and their behavior during close solar encounters. The possibility that Atlas might harbor internal structures that are hollow, or that its debris and fragment patterns are arranged in regular or organized configurations, could imply the presence of manufactured components. Such features would demand meticulous and extensive analysis before any findings could be confidently shared with the public. This cautious approach stems from the extraordinary nature of these potential indicators, patterns that could suggest artificial design rather than natural formation, necessitating rigorous verification to prevent premature or misleading conclusions. Adding to the intrigue is the spectroscopic data that the James Webb Space Telescope may have captured during its August 6th observation, a dataset that, as of now, remains unpublicized. The chemical makeup of Atlas's enormous carbon dioxide envelope should, in theory, be straightforward to analyze and confirm. Typically, such spectroscopic signatures are clear and distinctive, allowing scientists to determine the composition with relative ease. Yet, no definitive results have been released, leading to speculation about what mysteries they might contain. It's possible that the spectral lines reveal unusual isotopic ratios, variations in the relative abundance of isotopes, that do not align with known solar system materials. Such anomalies could suggest that Atlas formed under conditions unlike those in our local stellar neighborhood, hinting at a more exotic or unfamiliar origin. Further complexity arises from the reported green coloration observed in Atlas's coma. While at first glance it might seem a simple chemical signature, perhaps caused by the excitation of molecules like dicarbony or cyanide, the actual chemistry could be far more intricate. If detailed spectroscopic analysis uncovers the presence of synthetic compounds or isotopic signatures that point toward industrial or artificial processes, the implications would extend well beyond traditional comet science. It would raise profound questions about the nature of this object, potentially indicating technological artifacts masquerading as natural phenomena, rather than objects formed purely through cosmic natural processes. The mysterious anti-tail behavior exhibited by Atlas adds another layer of enigma. Under normal circumstances, a comet's tail and dust flow are driven by the solar wind and radiation pressure, creating structures that appear to be pushed away from the sun. However, Atlas's anti-tail, pointing directly toward the sun, suggests electromagnetic properties that might not be entirely natural. This could imply the use of artificial propulsion systems or electromagnetic fields designed to manipulate material flows, creating the illusion of defying natural physics. If Atlas employs controlled electromagnetic forces to steer or shape its coma and tail, this would indicate technology far beyond current human understanding, opening the door to possibilities of advanced extraterrestrial engineering. Examining Atlas's trajectory closely raises further questions: the alignment of its observed path with precise observational opportunities, such as its close encounter with Mars, the optimal distance at perihelion, and the favorable viewing windows from Earth, may not be purely coincidental. Instead, these could reflect deliberate course corrections or navigational adjustments, suggesting that someone or something might have planned these approaches for maximum observational advantage. Such geometries are rare and typically require intentional planning, especially for objects arriving from interstellar space, which normally follow more unpredictable or less optimized paths. Despite these provocative possibilities, it is essential to ground ourselves in official explanations provided by NASA and other space agencies. Their documentation clarifies that the observational gaps we are experiencing are, in fact, consistent with legitimate technical challenges. Solar conjunction, the period when Atlas aligns behind the Sun from Earth's perspective, introduces unavoidable viewing difficulties, temporarily impeding Earth-based observations. Additionally, telescope scheduling constraints, the natural delays inherent in data analysis pipelines, and the peer review process all serve to extend the timeline from observation to public release, especially for complex and unprecedented findings. Therefore, the current silence surrounding Atlas may not be the result of sinister concealment, but rather a reflection of due scientific caution. When confronted with phenomena that challenge our existing models, such as unusual outgassing behavior, anomalous tail structures, or chemical signatures, professional astronomers prefer to thoroughly understand these anomalies before making statements that could require later correction. This responsible approach ensures that conclusions are based on solid evidence, minimizing the risk of spreading misinformation. The intricate and unusual characteristics of Atlas, its potential internal architecture, chemical signatures, electromagnetic behaviors, and trajectory alignments, are all factors that can justify extended periods of detailed analysis. Such careful scrutiny, though it may appear suspicious to outside observers, is a hallmark of responsible scientific practice. Furthermore, international coordination among multiple institutions introduces additional delays. When various space agencies and research organizations must consolidate their findings and agree upon joint announcements, the process naturally takes time, further explaining the cautious pace of public disclosures. The European Space Agency, NASA, and other scientific organizations inherently require time to coordinate and synchronize their public releases, ensuring that information disseminated across various national and institutional channels remains consistent and accurate. This process, while necessary for maintaining scientific integrity, has historically been accompanied by a tradition of transparency, especially during the investigation of extraordinary phenomena. The cases of interstellar visitors such as Oumuamua and Borisov serve as important precedents. Their discovery and subsequent analysis benefited significantly from open, real-time scientific debate and public engagement. Such transparency not only fostered a better understanding of the discovery process, but also reinforced trust in scientific institutions. In contrast, Atlas's current pattern of more restricted information flow marks a disconcerting departure from this successful model of openness. It raises a fundamental question: are we witnessing a necessary form of scientific caution, an effort to thoroughly understand before revealing, or are we instead witnessing institutional fear, driven by concerns over potential public reactions that could challenge or destabilize long-held perceptions of our place in the universe? This question carries profound implications for the future of space exploration and the communication of cosmic discoveries. If the latter is true, that institutions are withholding information out of concern, They risk eroding public trust and undermining the collaborative spirit essential for humanity's ongoing exploration of the cosmos. Conversely, if the restraint is driven by legitimate scientific caution, it underscores the importance of meticulous verification, even if it delays public dissemination. Yet the most pressing concern remains. Will future revelations about extraordinary space phenomena be shared with the transparency and openness that have historically fostered understanding and curiosity? Or will secrecy become the new norm, casting a shadow over humanity's ability to act as informed, engaged partners in the unfolding story of cosmic discovery? In the coming days, the close-range imagery that Mars orbiters are poised to capture may provide the critical data needed to clarify Atlas's true nature. These images could either confirm that Atlas is an exotic yet ultimately conventional interstellar comet, an object that fits within our existing understanding, or they might reveal characteristics so extraordinary that they challenge everything we believe about interstellar visitors. When these images are finally transmitted and hopefully shared openly, they could revolutionize our perspective, forcing us to reconsider long-held assumptions. The universe, with its vast and mysterious dark spaces, holds secrets that we are only just beginning to glimpse. Atlas might represent merely the initial step in a series of discoveries that will compel us to expand our scientific horizons and redefine what is possible among the stars. The critical and most haunting question remains: are we truly prepared for such revelations? Will our institutions muster the courage and transparency necessary to share these truths openly? Or will fear and caution continue to overshadow the pursuit of knowledge? The way these upcoming discoveries are handled will not only shape our understanding of Atlas, but also determine whether humanity can maintain its role as an active, trusted participant in the ongoing exploration of our cosmic environment. Ultimately, whether we are ready or whether we can bear the truth may be the most profound and perhaps the most terrifying question of all.